The universe was never supposed to have structures this large. According to standard physics, matter should be evenly spread at the largest scales, but as we looked deeper into the sky, we found something else: walls of galaxies, chains of light, voids so vast they silence the theory behind them. In the next 3 hours, we will move through the most massive structures ever discovered, formations that stretch across billions of light years and raise questions modern cosmology still cannot fully answer. Before we begin, take a moment and tell us where you're listening from and what time it is for you right now. If quiet science helps you rest, consider subscribing so you never miss these deep journeys through space. Let's begin. We start with the largest structure ever recorded, mapped in the sky, measured in light, and still unexplained. Chapter 1. The Hercules, Corona Borealis Great Wall. In 2013, a group of astronomers studying gamma-ray bursts noticed something strange. They were mapping some of the brightest explosions in the universe, the signatures of distant stars collapsing into black holes. Each burst marked a violent death, a flare of energy from far beyond our galaxy, often from billions of years in the past. As the data came in, one region stood out. There was a cluster, not of stars or galaxies, but of bursts, dozens of them, tightly grouped, too many to be random. The team dug deeper. They plotted the distances, calculated the scale, and checked for errors. The result was staggering. These bursts were not scattered. They were arranged. They formed a single structure, a connected region of space more than 10 billion light-years across. It stretched through the constellations of Hercules and Corona Borealis, and it was bigger than anything previously known in the universe. They called it the Hercules Corona Borealis Great Wall. To put that scale in perspective, our Milky Way galaxy is about 100,000 light-years wide. That means this new structure was roughly 100,000 times larger than our galaxy. It was not a galaxy cluster. It was not a supercluster. It was something else entirely. A structure made of structures, an arrangement so vast that it exceeded the size limit allowed by standard cosmology. The universe has a rule. It is called the cosmological principle. It says that at a large enough scale, matter should be distributed evenly. There can be clusters, yes, even superclusters, but past a certain point, around 1 to 2 billion light-years, things should blur into smoothness. No more patterns, no more groupings, only statistical uniformity. But the Hercules Corona Borealis Great Wall broke that rule. It was more than 5 times larger than the theoretical limit, and yet there it was, not theorized but observed, mapped using real data. Its gamma-ray bursts were like lights on a bridge. Each one marked the location of a galaxy, and when you looked at them together, they formed a filament of unimaginable scale. This discovery created a quiet shock in the astrophysical community. If it was real, and not an illusion of data, it meant that something fundamental was missing from our understanding of how the universe is structured, because structures that large should not have had time to form. The age of the universe is estimated at around 13.8 billion years. Galaxies began forming about 400 million years after the Big Bang. To form something 10 billion light-years wide, you would need time for matter to coalesce, to gravitate, to clump together under gravity's pull. But that process takes billions of years, and it has limits. In most models, gravity simply doesn't have enough time to organize matter across such an enormous scale. The expansion of the universe fights against this process. The farther apart things are, the less they can influence each other. Gravity becomes weaker over distance, and the stretching of space itself pulls objects away. So to see such a massive arrangement, so early, is to glimpse something that should not be possible. Some scientists questioned the data. Could the gamma-ray bursts have been coincidental? Could observational bias or selection effects have skewed the findings? Maybe there was a denser region of the sky, better studied, with more bursts detected. The team checked for these possibilities, but even after corrections, the pattern held. The Hercules Corona Borealis Great Wall remained, larger than the Sloan Great Wall, larger than the huge LQG, larger than any structure ever found. The name Great Wall is more than poetic. It reflects how these formations resemble cosmic architecture, filaments of galaxies forming vast sheets and ridges across space. They outline the skeleton of the universe, connected by the invisible glue of dark matter. Between them lie voids, massive gaps with almost no galaxies at all. The universe, on its largest scales, looks like a sponge. It is not uniform. It is not chaotic. It is webbed. This is called the cosmic web, a structure made of structures, and the Hercules Corona Borealis Great Wall sits at the outer edge of what this web can contain. There is something deeply humbling about encountering such a thing, not just because of its size, but because of the silence around it. This structure is not near us. It is not even in our galactic neighborhood. Its light comes from over 10 billion years ago, a time when the universe was still young, and yet it was already arranged, already formed, already vast. it raises a profound question. If a structure this massive could exist at that time, then how many others might be out there, too distant to see, or too diffuse to detect? And what does it mean for the physics we rely on to describe the shape and behavior of the cosmos? Some researchers propose that these megastructures are statistical flukes, rare but not impossible. Others suggest we need to revise our models of cosmic inflation, or reconsider the assumptions of uniformity at large scales. Still others look toward the idea of dark matter playing a more complex role, or even the influence of unknown forces in the early universe. There is also the philosophical weight. We are small, infinitely so compared to this structure. Our planet, our solar system, even our galaxy, they are all local events. But here is something that connects galaxies across a tenth of the observable universe, and it was invisible until just a few years ago. What else lies hidden in the deep sky? What other patterns wait to be found, not in the stars themselves, but in how the stars are arranged? As we drift through this 3-hour journey, we will encounter many other structures, some known for decades, some newly discovered, and each one strange in its own way. But the Hercules Borealis Great Wall will always remain the largest ever recorded, a reminder that the universe is not just expanding, it is shaping itself, stretching beyond what we thought was allowed, and that somewhere in the distant sky, 10 billion light-years from here, a thread of structure still holds, longer than thought, older than expected, and far beyond what we once believed possible. Chapter 2. The Sloan Great Wall. In 2003, the Sloan Digital Sky Survey revealed something unexpected. It had been mapping hundreds of thousands of galaxies, not only noting their positions in the sky, but also measuring their distances through redshift data. This information was then used to construct one of the first detailed three-dimensional maps of the universe's structure at very large scales. What emerged from the data was not a uniform spread of galaxies, nor a random cloud of matter, but a coherent, elongated formation. It extended across more than 1 billion light-years. This structure would become known as the Sloan Great Wall. At the time of its discovery, the Sloan Great Wall was the largest known structure in the universe. It was composed of a filamentary network of galaxy clusters and superclusters, each cluster containing hundreds or thousands of galaxies, each galaxy containing hundreds of billions of stars. The wall was not a physical object like a solid barrier. Rather, it was a vast, gravitationally connected scaffold of luminous matter, shaped like a ridge cutting across the cosmic landscape. Its presence immediately raised questions about the limits of structure formation and the assumptions that shaped our cosmological models. One of the core principles of modern cosmology is that the universe should be homogeneous and isotropic on sufficiently large scales. This is known as the cosmological principle. It suggests that if one zooms out far enough, the differences between regions of space disappear and everything blends into a uniform distribution of matter. Local fluctuations are expected, such as galaxies, clusters, and superclusters, but at scales beyond a few hundred million light-years, those fluctuations should average out. No single structure should dominate or extend across more than 1 billion light-years. The Sloan Great Wall exceeded that scale. Its length was measured at approximately 1.37 billion light-years. That measurement alone made it difficult to reconcile with standard cosmological predictions. Simulations of structure formation, based on the gravitational collapse of matter seeded by early fluctuations in the cosmic microwave background, did not typically produce walls of that size. This raised a fundamental question: was the Sloan Great Wall an anomaly, a statistical outlier, or evidence that our models were missing something essential? Some scientists initially questioned whether it was truly a single structure. Could it be an alignment of several independent formations, coincidentally appearing connected due to our viewing angle? To investigate that possibility, astronomers performed statistical analyses, comparing the Sloan Great Wall's spatial coherence against randomly generated distributions of galaxies. The results showed that the structure's connectivity was too high to be explained by chance. Its existence was statistically significant. The clustering patterns were real. This was not a coincidence of perspective. It was a filament embedded in the cosmic web. That cosmic web is one of the most defining features of the universe on large scales. It is composed of filaments of matter, formed by the gravitational attraction of both visible and invisible mass. Dark matter, which outweighs ordinary matter by a factor of 5, provides the underlying scaffolding. Baryonic matter, the kind we see, flows along these filaments and pools at their intersections where galaxy clusters form. The Sloan Great Wall was not an isolated occurrence. It was part of this web, one of its longest and most well-defined threads. What makes the Sloan Great Wall particularly interesting is its orientation and composition. Unlike simpler structures, such as galaxy clusters, this wall spanned a three-dimensional region of space and connected multiple known superclusters, including the Coma supercluster and the Hercules supercluster. The density of galaxies within it was higher than the cosmic average, and its spatial extent suggested it had formed early and matured steadily under gravity's influence. Yet this evolution, given the scale, challenged existing theories. Could gravity alone have produced a structure this large within the 13.8 billion year age of the universe? The standard explanation for the formation of cosmic structures begins with tiny fluctuations in the density of the early universe. These fluctuations, measured in the cosmic microwave background, acted as seeds for the growth of larger structures. Over billions of years, under the influence of gravity, these seeds developed into galaxies, clusters, and eventually superclusters. However, the speed at which such large-scale formations could grow was constrained by the expansion of the universe and the rate at which matter could collapse. For something the size of the Sloan Great Wall to have formed naturally, it would require either an unusual early fluctuation or a revision of those constraints. As more large-scale structures were discovered, including the huge LQG, the South Pole Wall, and eventually the Hercules Corona Borealis Great Wall, the Sloan Great Wall began to look less like an isolated exception and more like a piece of a broader cosmic puzzle. These massive formations, though rare, kept appearing. Each one pushed the boundaries of theoretical possibility a little further, and each one reinforced the idea that the universe might be more structured, more connected, and less random than originally believed. The implications were not limited to astrophysics. They touched the foundations of cosmology. Was the cosmological principle still valid? Was the scale of homogeneity larger than we had assumed? Or was it a flawed assumption altogether? Some researchers argued for extending the scale of statistical homogeneity, suggesting that while the Sloan Great Wall exceeded the earlier predicted limit, the universe might still appear uniform at even larger distances. Others proposed deeper modifications to the underlying theories of structure formation, including the potential influence of non-Gaussian fluctuations, exotic physics in the early universe, or even variations in dark energy's behavior over time. There were also those who considered more radical ideas. One speculative hypothesis was that these large-scale structures could be signs of anisotropy in the fabric of space-time, that perhaps the universe is not truly the same in every direction. If true, this would have profound implications not only for cosmology but for physics as a whole. It would suggest that the rules governing cosmic evolution might depend on where and how you look. So far, the data does not confirm this, but the very need to ask the question reveals the depth of the mystery. For the scientific community, the Sloan Great Wall became a case study, a structure so large and well-defined that it could no longer be explained away. Its presence in the data was clear, its boundaries were mapped, its impact on theoretical models was undeniable. Whether or not it signaled the breakdown of existing theories, it certainly marked the point at which observational cosmology began to challenge the assumptions that had stood for decades. The name Great Wall carries with it a kind of reverence. It is a reminder that the universe is not a uniform haze. It is built, not with stone or steel, but with gravity, dark matter, and time. The Sloan Great Wall is not just a structure, it is a monument to the scale of natural architecture. It stretches across an invisible frontier, anchoring galaxies in position, carving shape into the cosmic fabric. We cannot see it with our eyes. It is too far. Its light took over 1 billion years to reach us. But through the careful mapping of galaxies, through measurements of redshift and clustering, we can reconstruct its shape, we can trace its presence in 3 dimensions, and we can feel, through data and silence, its overwhelming scale. It is not the largest structure we know of, but it was the first to truly shift our understanding of what the universe is capable of building. It opened the door to other discoveries, and it taught us to look deeper, not just for more galaxies, but for the patterns that connect them, because in those patterns, something unexpected emerges, a kind of quiet order rising from the apparent chaos of space. As we continue, we move back slightly in time, to the late 1980s, when a different survey revealed the existence of yet another Great Wall. This one came earlier, but its implications were just as bold. It was called the CFA2 Great Wall, and it would become the first structure to make cosmologists wonder whether there might be something very wrong with how we thought the universe was built.
Chapter 3. The CFA2 Great Wall. Before the Sloan Digital Sky Survey revealed its cosmic wall, before the Hercules Corona Borealis Great Wall challenged the very limits of scale, there was another structure that first shook the foundations of observational cosmology. It appeared in the 1980s at a time when the idea of mapping galaxies in 3 dimensions was still relatively new. It came from a survey known as the CFA Redshift Survey, a project that for the first time allowed scientists to see not just where galaxies were in the sky, but how far away they were. With that depth, a new vision of the universe began to emerge. The CFA2 survey, a continuation of the original project, produced a map that revealed something astonishing. Rather than an even cloud of galaxies, the data showed arcs, clusters, and threads, and among those patterns was a structure so vast and continuous, it stretched across a significant portion of the observable universe, a filament of galaxies measuring over 500 million light-years in length. At the time, this was the largest known structure in the cosmos. They called it the CFA2 Great Wall. It wasn't just the size that caught attention, it was the clarity. The wall stood out against the surrounding data, a sharp ridge of clustered galaxies forming a band that spanned across the survey's field of view. Unlike earlier models that assumed large-scale randomness, this wall looked deliberate. It curved slightly, suggesting a coherent structure, as if galaxies had been gently pulled into place over billions of years. The existence of this structure presented a dilemma. According to the cosmological models available at the time, the universe should appear homogeneous on scales beyond about 250 million light-years. The CFA2 Great Wall was twice that length, and it was not diffuse. It was dense, consistent, and too well organized to ignore. Its discovery forced cosmologists to reconsider their assumptions about large-scale structure formation. The key to the CFA2 survey's success was the use of redshift, the phenomenon where light from distant objects shifts toward longer wavelengths as they move away due to cosmic expansion. By measuring this redshift precisely, researchers could determine not only the angular position of a galaxy, but also its distance from Earth. This three-dimensional information was essential. It transformed our understanding of the cosmic landscape from a flat map to a volumetric space. As the data accumulated, the filamentary structure became increasingly evident. The galaxies within the CFA2 Great Wall were not isolated. They were gravitationally related, flowing together in a massive, coherent sheet. It was like seeing the skeleton of the universe for the first time, a glimpse of how galaxies actually arranged themselves over time, not just by accident, but by deep underlying forces. This wall connected several major galaxy clusters and included regions of notable density. Among them was the Coma cluster, a well-known supercluster of galaxies that itself played a central role in early research on dark matter. Its location within the wall suggested a kind of anchoring point, a gravitational node where matter accumulated along the filament. The wall was not continuous in the way a physical surface is. It had gaps and pockets, regions of lower density, but overall the structure held together. It defied the expectation that at such scales, matter should be evenly spread. Instead, it formed an architectural band across space, evidence that the universe's expansion had not washed away all order. When this discovery was first presented to the scientific community, it was met with both excitement and skepticism. Some argued that the wall might be a visual illusion created by selection effects or limited data, but further analysis confirmed the structure's validity. Statistical models showed that the distribution of galaxies within the wall was not random. It followed predictable clustering patterns that could not be easily explained away. The CFA2 Great Wall also inspired new theoretical work. If a structure of that magnitude could form under gravitational influence, then what were the boundaries of possibility? Could walls even larger than this exist? And if so, would they challenge the cosmological principle, or would they simply shift the scale at which homogeneity emerged? Some cosmologists proposed that the CFA2 Great Wall marked the outer limit of meaningful structure. They argued that while larger filaments might exist, their density would be lower, and their presence would not significantly disrupt the overall uniformity of the universe. Others were less convinced. They saw the wall as the beginning of a trend, an indication that larger structures were not only possible, but inevitable. From a data perspective, the CFA2 wall was the first structure to show how galaxy redshift surveys could reshape our understanding of space. The visualization was striking, a wedge-shaped diagram, known as a redshift cone, in which the wall appeared as a bold, arching stripe of galaxy points. This cone became one of the most iconic images in modern cosmology, not because of its artistic quality, but because of the scale it revealed. This was not a picture of a few galaxies, it was a picture of the universe's underlying geometry. The discovery also opened the door to larger and deeper redshift surveys. Future projects would build on the same technique, extending the map to greater distances and higher precision. The Sloan Digital Sky Survey, for example, was directly inspired by this kind of structure. Its goal was to map the universe more completely, to see whether the CFA2 Great Wall was an isolated event, or part of a deeper, hidden pattern of cosmic architecture. Eventually, larger structures were discovered, but the CFA2 Great Wall still holds a unique position. It was the first structure to break the psychological barrier of scale. Before its discovery, the idea of a billion light-year-long filament was almost science fiction. Afterward, it became a serious question for astrophysics. What also makes the CFA2 Great Wall notable is that it was discovered during a time of technological limitation. Computing power was modest, instruments were less sensitive, data processing was slower, and yet, even with those constraints, the structure emerged clearly. It was not buried in noise. It was not an ambiguous statistical artifact. It stood plainly within the data, challenging what scientists believed about the universe's limits. The wall also reinforced the concept of the cosmic web, a term that would later come to dominate discussions of large-scale structure. Filaments, walls, and voids are now considered fundamental features of the universe's shape. Simulations of cosmic evolution, such as the Millennium Simulation and the Illustris project, have since confirmed that these patterns are not theoretical abstractions. They are real outcomes of gravitational interaction in an expanding universe. Still, there are questions the CFA2 Great Wall left unanswered. Could such structures have formed faster than models suggest? Is dark matter more dynamic or structured than current theories propose? Do initial conditions from the early universe imprint larger-scale patterns than we've accounted for? These remain open fields of study, but the wall itself stands as a reference point, a structure that invites further questions without offering a complete answer. And perhaps that is why it matters so much. It is not only large, it is also unresolved. In terms of visibility, the CFA2 Great Wall is relatively nearby in cosmic terms. Its light does not travel billions of years to reach us. It is part of our local supercluster region, which means it offers a unique opportunity to study the detailed physics of structure formation close to home. Its proximity also means we can observe the individual galaxies that compose it, and not just their statistical shadows. That ability to study both the whole and its parts makes the CFA2 Great Wall a kind of cosmological classroom. It bridges the gap between data and theory, between observation and simulation, and while it no longer holds the title of the largest structure, it remains the one that shifted our understanding of what large could truly mean. Now we move forward to another strange discovery. Not a wall this time, but a ring. A circular arrangement of gamma-ray bursts so vast, so symmetrical, that some have questioned whether it could even be real. We continue with the story of the giant GRB ring, and the mystery of patterns that seem too precise for randomness alone.
Chapter 4. The Giant GRB Ring. In 2015, a study of gamma-ray bursts revealed something deeply unexpected. Gamma-ray bursts, or GRBs, are among the brightest and most energetic events in the known universe. They are caused by the deaths of massive stars or the merging of compact objects such as neutron stars. Because they shine so brightly and briefly, often lasting only seconds, they are detectable across billions of light years, even from the early universe. This makes them valuable tools for astronomers. They act as cosmic lighthouses, illuminating the farthest corners of space and time. Researchers studying these bursts began to notice an unusual concentration in a specific region of the sky. There appeared to be 9 gamma-ray bursts, all located roughly the same distance from Earth, arranged in what seemed to be a circular pattern. Each burst was between 6.5 and 10 billion light-years away, and taken together, they formed an enormous ring-like structure in three-dimensional space, a formation that became known as the giant GRGB ring. Its diameter was estimated at over 5 billion light-years, placing it among the largest apparent structures ever detected. Unlike the Sloan Great Wall or the CFA2 Great Wall, which were formed from visible galaxies and clusters, this ring was composed of transient signals, each one representing a powerful death event, not a steady source of light. Yet despite their individual randomness, these bursts were statistically grouped. Their arrangement was too symmetrical to be dismissed as coincidence. At first, the researchers were cautious. After all, gamma-ray bursts are rare. Their apparent grouping could have been the result of an observational bias or random clustering, but when simulations were run to estimate the likelihood of such an arrangement occurring by chance, the results were surprising. There was less than a 0.1% probability that this ring-like formation was random. The odds suggested a real, coherent structure, or at the very least, a coordinated event in the early universe that led to this pattern. This finding created tension with the cosmological principle once again. According to our understanding of the large-scale universe, there should be no structure beyond roughly 1 to 2 billion light-years in diameter. Past that scale, matter should appear evenly distributed. The giant GRGB ring, at over 5 billion light-years across, challenged that assumption. But gamma-ray bursts are not bound together in the way galaxies are. They do not form gravitational clusters. They are individual explosions, remnants of stellar collapse. So how could they be arranged in a ring? One possibility is that the structure is not truly circular in space, but appears ring-like because of our perspective, a projection of a larger three-dimensional shell or filament onto a two-dimensional view. Another possibility is that the bursts occurred in galaxies that themselves were arranged along a curved filament or wall. The researchers proposed that the ring might reflect an underlying distribution of galaxies or matter that we have not yet detected directly. If galaxies along a curved cosmic filament happen to produce gamma-ray bursts at similar times in cosmic history, the result would be a ring-like shape from our point of view, but that would still imply an underlying structure on the same scale as the ring itself, which again violates current theoretical limits. There is also the question of timing. These bursts did not occur simultaneously. Each one took place in its own galaxy, in its own moment, billions of years ago, but because they are all located at roughly the same distance, their light is reaching us now, giving the impression of coordination, even though the events themselves were separated by time. This leads to an important distinction. The giant GRB ring is not a structure in the conventional sense. It is a pattern, a statistical clustering of extreme cosmic events that suggests some larger-scale ordering of matter. Whether it is a physical ring, a projection, or a coincidence amplified by human pattern recognition is still debated. but its existence, or even its strong possibility, invites deeper exploration of the large-scale distribution of both visible and invisible matter. If the ring is real, it may point to a vast network of galaxies and dark matter extending over 5 billion light-years. Such a structure could be an arc of a larger cosmic filament, part of the vast skeleton that holds the universe together. If true, it would suggest that not only do galaxies form along these filaments, but also that extreme events, like gamma-ray bursts, are more likely to occur in certain regions of that structure. The question then becomes, why? What causes this spatial preference? Are there conditions along these filaments, such as high-density environments or rapid star formation, that make gamma-ray bursts more common? Or are we seeing the relic of something even older, an echo of how matter cooled and clustered in the early universe? Some researchers have suggested that the ring could be a signature of Baryon Acoustic Oscillations, the regular spacing of matter in the early universe caused by sound waves moving through the hot plasma shortly after the Big Bang. These oscillations left imprints in the distribution of galaxies and perhaps also in the conditions that led to gamma-ray burst activity. But the scale of the GRB ring does not match standard predictions of baryon acoustic features. It is too large, too coherent, and too symmetrical. There is also the possibility of a cosmic void surrounding the ring. If the region beyond the ring's boundaries is underdense, a vast zone with fewer galaxies, it could amplify the appearance of the ring-like structure by contrast. This idea has parallels with other large-scale structures, such as the Boötes Void or the KBC Void, where emptiness itself helps define the presence of neighboring filaments and walls. Whatever the explanation, the giant GRB ring is a reminder of how much we still do not know. It was discovered not through direct imaging or traditional galactic surveys, but through the observation of brief, violent flashes of light, the deaths of massive stars. From those brief moments, a structure emerged, visible not in light but in pattern, not in permanence but in echoes. The pattern itself is fragile. It depends on a small number of data points, 9 gamma-ray bursts. That is not many, given the vastness of space, but even so, their alignment is statistically powerful, enough to warrant study, enough to challenge assumptions. Some in the scientific community remain skeptical. They argue that without more data, it is premature to claim a large-scale structure based on so few events. Future gamma-ray observations, especially with more sensitive detectors, may help confirm or refute the ring's existence. If more bursts are discovered that fall along the same pattern, the statistical weight of the structure will grow. If not, it may fade into coincidence. But even as a tentative structure, the giant GRB ring plays an important role in modern cosmology. It broadens the set of tools we use to understand the universe's shape. It reminds us that structure is not always visible. Sometimes it is revealed through timing, through bursts, through the scattered, silent deaths of stars. And it connects to a larger idea that the universe may contain arrangements beyond our current imagination, not just walls and filaments, but rings, arcs and shells, not only galaxies and clusters, but patterns defined by events, by brightness, by age. The giant GRB ring, if confirmed, would not only be a new kind of structure, it would be a challenge, a test of whether our models of the early universe are flexible enough to explain what we find, not just in the matter that remains, but in the light that fades. As our telescopes continue to watch the sky for these brief flashes, we will gather more data, more distances, more moments of collapse and light. Perhaps more rings will appear, perhaps this one will disappear, but either way, the universe continues to signal, and we continue to listen.
Chapter 5. The South Pole Wall. For decades, a large region of the night sky remained poorly mapped, not because it was distant or faint or unreachable, but because it sat behind the thick, glowing plain of the Milky Way. This area, obscured by dense clouds of interstellar dust and countless stars, is known to astronomers as the zone of avoidance. It is not empty, it is not dark, it is simply hidden, a blind spot created by the galaxy we live in. For a long time, the zone of avoidance made it difficult to complete maps of the cosmic web. Surveys that traced the distribution of galaxies often had to skip this region or rely on estimates. And so, for years, cosmologists wondered what might be lurking behind the veil of our own galaxy. What structures might have gone unnoticed, not because they were distant, but because we happened to be looking through the crowded core of the Milky Way itself. In 2020, that question gained a remarkable answer. Using data from redshift surveys, velocity fields, and infrared observations that could pierce through galactic dust, astronomers uncovered a massive filament of galaxies hiding behind the zone of avoidance. This structure, later named the South Pole Wall, was found stretching across more than 1.3 billion light-years of space. And it wasn't far away. It was surprisingly close to our own galactic neighborhood, almost directly beneath us in celestial coordinates. The South Pole Wall is now considered one of the largest known structures in the local universe. It spans a colossal arc across the sky, connecting various clusters and superclusters in a dense ribbon of matter. It includes portions of the Parvo-Indus supercluster and threads through several other known galactic groupings, but until recently it had gone undetected. Its discovery was not the result of a new telescope or a single dramatic observation. It was the product of careful reconstruction, a map built from pieces, assembled slowly by tracing the motion of galaxies affected by its gravitational pull. Galaxies do not simply float in space, they move, and their motion is influenced by the gravitational landscape around them. This concept is known as the cosmic velocity field, the study of how galaxies deviate from the uniform expansion of the universe due to the gravitational influence of nearby structures. By observing how galaxies move relative to the Hubble flow, scientists can infer the presence of hidden mass, even when it cannot be seen directly. The South Pole Wall revealed itself not in light, but in motion. Galaxies on either side of it appeared to be flowing toward its dense ridge. This pattern, visible in the velocity field data, was the signature of a gravitational structure, one that had been there all along, pulling galaxies subtly over millions of years, yet invisible until now. When astronomers plotted its full shape, the South Pole Wall appeared as a long winding filament, curving behind the Milky Way's plane and extending outward toward the southern sky. It was found to enclose a giant void on one side, an empty region of space hundreds of millions of light-years wide. On the other side, it bordered several major clusters, acting as both a boundary and a bridge within the cosmic web. The discovery of this wall came at a time when the mapping of the universe had become more refined than ever before. Surveys such as Cosmic Flows 3 and the 2-micron All-Sky Survey provided essential data, including redshift measurements and near-infrared observations, that allowed astronomers to see through the obscuring dust of the Milky Way. Combined with improved models of galaxy motion, this data revealed a structure that was not distant or theoretical, but part of our immediate cosmic environment. The fact that such a massive formation could remain hidden until recently speaks to the limits of our perspective. Even as we peer deep into the early universe, tracing light from billions of years ago, there are still vast regions nearby that we have yet to fully explore. The South Pole Wall reminds us that sometimes the most significant discoveries are not at the edges of space, but just beyond the horizon we thought we had already crossed. In terms of structure, the South Pole Wall is similar to other filaments in the cosmic web. It is composed of thousands of galaxies, grouped into clusters and linked by flows of matter along gravitational channels. The galaxies within it show evidence of interaction, with signs of past mergers, tidal distortion, and active star formation. This suggests that the wall is not only a passive feature, but a dynamic environment where galaxies continue to evolve. Its location near the edge of the Laniakea supercluster, the structure that includes our own Milky Way, raises further questions about how superclusters and walls connect. Is the South Pole Wall an extension of Laniakea? Is it part of an even larger filament network that remains partially hidden, or does it serve as a boundary between distinct gravitational domains? At this scale, the distinction between a wall and a supercluster becomes subtle. Both represent dense regions of the universe's large-scale matter distribution, but walls are typically longer, thinner, and more linear, while superclusters are more spheroidal and clustered. The South Pole Wall appears to straddle that line, a structure that defines space, not through brightness, but through gravity and flow. What makes this wall particularly interesting is how it reshapes our understanding of the local universe. The Milky Way sits within a complex web of matter, and for decades we believed we had identified the major features of that web. But with this discovery, we are forced to reconsider the extent of our cosmic neighborhood. It's possible that the South Pole Wall is just one segment of a larger, previously hidden structure, one that may continue far beyond what we have currently measured. The structure also highlights the role of voids in shaping the universe. Large-scale filaments do not exist in isolation. They are formed, stretched, and supported by the vast empty regions around them. The South Pole Wall borders a significant underdense region, which may have contributed to its development by pushing matter into denser lanes through gravitational collapse. In this sense, the void is just as important as the wall, not through presence, but through absence. Understanding the motion of galaxies near the South Pole Wall also has implications for studying dark matter, because most of the wall's gravitational influence cannot be explained by visible matter alone. Its effects provide indirect measurements of dark matter's distribution. By modeling how galaxies flow toward the wall and how the wall interacts with neighboring structures, researchers can refine simulations of dark matter filaments that extend beyond the reach of light. As with many large-scale structures, the South Pole Wall invites more questions than answers. Was it always this large, or has it grown slowly over time? Did it form early, seeded by density fluctuations shortly after the Big Bang? Or is it the result of more recent cosmic evolution, shaped by interactions with nearby voids and clusters? The answers lie not just in one observation, but in years of careful mapping, data aggregation, and statistical modeling. Future surveys may reveal even more. Telescopes like the Vera C. Rubin Observatory, which will map the entire southern sky in unprecedented detail, could uncover additional portions of the wall or reveal similar structures nearby. New infrared missions may further reduce the zone of avoidance avoidance, allowing us to see through the Milky Way's dust with greater clarity, and gravitational wave observatories may even detect ripples from galactic collisions within the wall, offering another dimension of data. For now, the South Pole Wall stands as one of the largest features ever found so close to Earth. It was always there. It shaped the motions of galaxies. It defined the boundary of our supercluster, but we only noticed it once we learned how to look through the light of our own home. And this is perhaps the most profound lesson of the South Pole Wall, that the universe is not always hidden by distance. Sometimes the greatest mysteries lie just beyond the glare of the familiar. Sometimes discovery is not about traveling farther, but about seeing more clearly.
Chapter 6. The Shapley Supercluster. In the southern sky, far beyond the glowing haze of the Milky Way, sits one of the most massive structures ever discovered in the observable universe. It is not a wall, it is not a ring, it is a supercluster, a densely packed region containing thousands of galaxies, dozens of clusters, and a gravitational pull so immense it is believed to be influencing the motion of entire galactic regions. This formation is called the Shapley Supercluster, named after the American astronomer Harlow Shapley, who first began identifying unusually dense regions in the direction of the constellation Centaurus. Today, this supercluster remains one of the largest and most studied high-density concentrations of matter within a distance of 1 billion light-years from Earth. Unlike the sprawling filaments and walls seen in other cosmic structures, the Shapley supercluster appears compact, as if the universe itself had pressed matter inward at this location. It contains more than 8,000 galaxies, spanning over 650 million light-years across. But what makes the Shapley supercluster unique is not just its scale, it is its density. Within its central regions, the number of galaxies per cubic megaparsec is significantly higher than the cosmic average. This gravitational well acts as a kind of anchor, pulling nearby clusters and affecting the motion of galaxies across hundreds of millions of light-years. When scientists map the motion of galaxies in our local universe, they observe something peculiar. Our Milky Way, along with the entire local group and neighboring clusters, is moving toward a specific region in space, a drift known as the dipole anisotropy in the cosmic microwave background. This motion is not fully explained by nearby structures alone. The gravitational pull from the Virgo cluster and the Laniakea supercluster cannot entirely account for it, but when the mass of the Shapley supercluster is included in the calculations, the numbers begin to make sense. This has led to the idea that the Shapley supercluster is part of what's called the Great Attractor, a mysterious region of space exerting a massive gravitational pull on galaxies, including our own. While the exact nature of the Great Attractor remains debated, the Shapley supercluster stands as one of its most likely central components. Its mass is estimated to be more than 10 million billion times that of our Sun. It is not simply another structure, it may be part of the reason our entire region of space is in motion. The Shapley supercluster includes several major galaxy clusters, among them the Abell 3558 cluster, which itself contains over 100 large galaxies. Other clusters include Abell 3562, Abell 3571, and Abell 3556. These clusters are interconnected, linked by gravitational bridges and streams of matter. Each contains elliptical galaxies, spiral galaxies, and active galactic nuclei. Some of the galaxies are merging, others are forming stars at high rates, indicating that the region is still evolving dynamically. Observations from X-ray telescopes have revealed that many of these clusters are embedded in a hot intracluster medium, gas heated to millions of degrees, glowing faintly in the X-ray part of the spectrum. This hot gas provides further evidence of interactions and collisions among galaxies and clusters, which release energy and create turbulence in the surrounding space. The Shapley supercluster is a rich laboratory for understanding both cosmic structure and galaxy evolution. Its extreme density allows scientists to study how environment affects galaxies, whether they become stripped of gas, whether they interact more frequently, and how their shapes and star formation histories differ from those in more isolated regions. In essence, the Shapley supercluster is not just a structure, it is a living system, shaped by gravitational forces, enriched by interactions, and constantly influenced by the dark matter scaffold that holds it all together. Despite its apparent compactness, the Shapley supercluster is still just one part of the larger cosmic web. It sits near the edge of several other filaments, and its influence extends into regions that connect with the Centaurus and Hydra superclusters. These connections are not just visual, they are gravitational. Galaxies follow paths shaped by invisible threads of matter, and many of those paths point toward the gravitational well of Shapley. Simulations suggest that over billions of years, this supercluster will continue to draw in galaxies from surrounding regions. It may eventually become part of a larger structure, a gravitational sink where galactic material coalesces into one dense node. At that point, the structure may no longer be a supercluster by today's definitions, but something more extreme, a massive galactic city forming the core of a future cosmic megastructure. In the context of the expanding universe, this kind of accumulation seems paradoxical.
If space is stretching, why are galaxies still moving together? The answer lies in the balance between cosmic expansion and local gravity. On the largest scales, galaxies are receding from one another due to the expansion of space, but in regions of high density like the Shapley supercluster, gravity overwhelms expansion, matter pulls itself inward, and in doing so it creates islands of structure in an ocean of growing distance. From Earth, the Shapley supercluster is not easily visible. Its location in the southern sky means it is best observed from the southern hemisphere, and because much of it lies behind the Milky Way's bright center, it was not fully mapped until multi-wavelength surveys, including infrared and X-ray observations, helped fill in the gaps. Today, however, its shape and influence are clear. It is a gravitational heavyweight, and its effects ripple across space. One of the most fascinating implications of this structure is its role in the cosmic flow of galaxies. Our local group, which includes the Milky Way and Andromeda, is part of a larger movement toward the Shapley supercluster. This motion is not uniform. It combines with flows toward other nearby structures, but over time, trajectories point toward Shapley as one of the dominant centers of mass. In this way, the Shapley supercluster acts like a quiet engine. It does not emit much light itself, it does not dominate the sky, but it shapes the paths of thousands of galaxies. It bends motion, it pulls on space, and it reminds us that gravity, even across unimaginable distances, still leaves its mark. The presence of such a dense region also has implications for the study of dark matter. To produce the observed velocities and clustering within Shapley, the amount of visible mass, stars and gas is not enough. Dark matter must provide the scaffolding. Its gravitational pull binds the clusters together and allows the structure to resist the stretching effect of universal expansion. By studying the velocities of galaxies and the temperature of X-ray gas, astronomers can estimate the total mass and from there infer the distribution of dark matter. Even as more massive structures are discovered at greater distances, the Shapley supercluster remains important for one reason above all. It is close. Its proximity means we can study it in detail, observe individual galaxies, trace star formation histories, and measure cluster masses with high precision. It is a case study in how cosmic structure builds itself, not just in theory, but in real space. In many ways, the Shapley supercluster marks a bridge in our exploration of scale. It is not as expansive as the cosmic walls and giant voids found deeper in the universe, but it is more intimate. Its closeness makes it tangible, and its density makes it undeniable. It is a statement that gravity never truly stops working, even when galaxies are billions of years old and the universe itself is stretching in all directions.
Chapter 7. The Boötes supercluster complex. As we continue mapping the largest known structures in the universe, we arrive at something less sharply defined, but no less important. The previous structures we explored, walls, rings, and superclusters, each had clear shapes, centers of mass, and measurable gravitational influence, but now we encounter something different, a vast, extended chain of galactic matter that spans more than 1 billion light-years, without a single core or simple geometry. It is not a wall, it is not a cluster, it is a complex, a long interconnected web of superclusters and filaments known as the Boötes supercluster complex. First proposed in the late 1980s, this structure was recognized as a series of connected galaxy clusters and superclusters stretching across the sky from the constellation Pisces through Boötes and beyond. The complexity of its form defied traditional naming conventions. It was neither centralized nor clearly bounded, yet it was continuous. Its scale was extraordinary, with its known extent reaching well beyond 1 billion light-years. Within this enormous span are several major superclusters. Among them are the Pegasus-Pisces supercluster, the Boötes supercluster, and parts of the Sculptor Wall and Perseus-Pisces filament. Each of these substructures contains hundreds or even thousands of galaxies. But what distinguishes the Boötes complex is not the size of any single part, it is the way all the parts are connected. They are not isolated clusters, but components of a much larger whole, bound by threads of dark matter and drawn together by gravity over billions of years. The filaments that link these regions are long and often diffuse. Galaxies are distributed along them like beads on a string, with clusters forming at intersections where matter accumulates. These filaments can extend hundreds of millions of light-years, curving gently through space, sometimes bridging vast cosmic voids. When mapped in 3 dimensions, they appear like veins in a vast circulatory system, not random, but delicately arranged by forces we still do not fully understand. The Boötes supercluster complex also includes the Perseus-Pisces supercluster, a particularly rich and well-studied region that stretches across much of the northern sky. It lies at a distance of roughly 250 million light-years from Earth, and its filament extends more than 300 million light-years in length. This portion of the complex contains several massive galaxy clusters, including Abell 262, Abell 347, and Abell 426. Each of these clusters is embedded in the larger filament, moving not independently, but as part of a broader gravitational flow.
What makes this complex so important is that it provides one of the clearest examples of how structure scales upward in the universe. Galaxies form groups, groups form clusters, clusters form superclusters, and superclusters in turn do not stand alone, they gather into complexes. This hierarchical assembly is not simply a feature of observation, it reflects how matter behaves under the influence of gravity across cosmic time. The existence of such a large and intricate structure also raises important questions about cosmic evolution. How did these clusters come to be connected? Did they form independently and later merge through gravitational attraction, or were they always part of a single stretched-out seed in the early universe, where a primordial overdensity led to the coalescence of matter along a particular direction? Simulations of structure formation suggest that both processes may play a role. Initial fluctuations in the cosmic microwave background gave rise to regions of slightly higher density. These regions collapsed under gravity, forming the seeds of filaments and clusters. Over billions of years, these structures evolved, feeding off their surrounding environment, drawing in more matter, and creating the vast complex we observe today. The Pisces-Cetus supercluster complex is not a uniform formation, its density varies. Some sections are rich with galaxies, others are sparse, bordering the edges of deep cosmic voids. This patchiness is expected, as gravitational collapse does not occur evenly. Instead, it depends on initial conditions, local density, and the flow of dark matter, which acts as the invisible framework for luminous matter to gather upon. Dark matter simulations have shown that these large-scale filaments are real, not just statistical artifacts. The cold dark matter model predicts their emergence, and their existence is one of the strongest pieces of observational evidence supporting current cosmological models. Yet the specific shapes and arrangements we see, such as those within the Pisces-Cetus complex, still contain surprises. They are more structured than randomness would allow, but more chaotic than simple geometry would predict. Part of what makes the Pisces-Cetus region so intriguing is that it is close enough to allow detailed study. Its proximity enables us to observe galaxies in individual clusters with high resolution, to map redshifts accurately, and to analyze the gravitational interactions between neighboring superclusters. This level of detail has been essential for testing cosmological models, especially those dealing with dark energy and the expansion rate of the universe. One of the ways astronomers study these complexes is through redshift surveys. These surveys measure how fast galaxies are moving away from us, allowing researchers to determine not just distance, but the local velocity field, a map of how galaxies move under gravitational influence. In the Pisces-Cetus region, these measurements have revealed coherent flows of matter along the filaments, moving slowly inward toward denser regions. These motions are signatures of gravitational collapse, proof that the structure is still evolving. Even now, billions of years after its formation, the complex is not static. Galaxies continue to fall into clusters. Clusters merge, mass accumulates, the cosmic web is alive with motion, and the Pisces-Cetus supercluster complex is one of its most active regions. There is also something humbling about the structure's sheer scale. When we consider that our own Milky Way is just one galaxy, in a small group called the Local Group, which is part of the Virgo cluster, which itself belongs to the Laniakea supercluster, we begin to see just how vast the Pisces-Cetus complex really is. It links together multiple superclusters like Laniakea, stretching across a significant portion of the observable universe. The name complex may seem understated, but it reflects a reality of cosmic cartography. Not all structures have clear edges or central points. Some are better understood as collections, interlinked systems that defy simple description. The Pisces-Cetus supercluster complex is one such entity. It is defined not by what it contains, but by how its contents are arranged in relation to one another. This shift in perspective from discrete objects to relational patterns marks an evolution in how we understand the universe. It's no longer enough to count galaxies or identify clusters. We must look at how everything connects. Where are the filaments? Where are the voids? Where do the flows converge? And what does that tell us about the universe's origin and fate? One of the most interesting features of the Pisces-Cetus complex is its connection to large cosmic voids. Between the filaments are enormous underdense regions, areas where few galaxies exist. These voids are not just empty space, they are shaped by the gravitational tug-of-war between nearby structures. As mass collapses into filaments and clusters, voids expand, pushing against each other and deepening in response to the structure growing around them. In this way, voids help sculpt the shape of the complex. They create boundaries, they guide the paths of matter, and they enhance the contrast between empty and full, highlighting the presence of structure where it exists. The study of voids and complexes together has become a major focus in cosmology. It allows researchers to refine models of dark energy, to test the predictions of general relativity, and to probe the initial conditions of the universe. Structures like the Pisces-Cetus complex are not just scenery, they are test beds. They hold the imprints of ancient physics, and they offer clues about what the universe is made of, how it behaves, and what its future might hold.
Chapter 8. The Coma Supercluster. In the northern sky,
Between the constellations Coma Berenices and Virgo lies a region of space that has played a central role in how we understand large-scale structure in the universe. It is not the largest known formation, it is not the most distant, but it is among the most detailed, most accessible, and most influential in the development of observational cosmology. This region is known as the Coma supercluster, and within it sits one of the densest galaxy clusters ever observed. The Coma cluster, officially named Abell 16056, is at the heart of the Coma supercluster. It is located roughly 320 million light-years from Earth and contains over 1,000 identified galaxies. Most of these galaxies are ellipticals, large, smooth, and nearly featureless in appearance, suggesting they are old and have undergone many mergers. The Coma cluster itself spans several million light-years in diameter and has a mass exceeding 1 quadrillion solar masses. It is not only a local gravitational center, but also a historical reference point, one of the first places where the existence of dark matter was inferred. In the 1930s, astronomer Fritz Zwicky was studying the velocities of galaxies within the Coma cluster. Using the virial theorem, he compared the visible mass of the galaxies to their motion. What he found was startling. The galaxies were moving too fast to be gravitationally bound by their visible mass alone. If only the stars and gas could account for the gravitational pull, the cluster should have dispersed long ago. Zwicky concluded that there must be an unseen form of matter holding the cluster together. He called it dunkel materie, dark matter. It was one of the earliest suggestions that the majority of matter in the universe is invisible, interacting only through gravity. The Coma supercluster itself extends well beyond the Coma cluster. It includes nearby structures such as the Leo cluster, Abell 2199, and the Keynes-Venatici cluster, forming a large interconnected region with multiple high-density zones. These clusters are connected through filaments of galaxies, bridging gaps across tens of millions of light-years. As with many parts of the cosmic web, the supercluster is not a uniform shape, but rather a textured three-dimensional scaffold. It contains rivers of galaxies, pools of dark matter, and currents of hot intergalactic gas. The Coma supercluster is part of a broader complex of nearby structures that also includes the Virgo supercluster, the one that houses our own Milky Way. Together, these form part of the Laniakea supercluster, a larger gravitational basin that encompasses many local galaxy clusters and filaments. Though our galaxy lies closer to Virgo, the Coma supercluster represents a denser, more massive region. Its gravitational influence stretches far beyond its immediate boundaries, contributing to the motion of neighboring clusters, including our own. One of the defining features of the Coma cluster is its X-ray brightness. Observations by space telescopes such as Chandra and XMM Newton have revealed a glowing halo of hot gas surrounding the cluster. This gas reaches temperatures of tens of millions of degrees Kelvin and emits strongly in the X-ray part of the spectrum. The source of this heat is gravitational. As matter falls into the cluster's deep potential well, it accelerates and compresses, causing friction and heating the gas to extreme temperatures. This hot intracluster medium is more massive than all the stars in the cluster combined, and yet, even when the mass of the hot gas is included, it still cannot account for the gravitational binding of the cluster. This is one of the clearest pieces of observational evidence for dark matter. The visible galaxies and glowing gas tell only part of the story. The rest lies in a shadow map, a distribution of mass that does not shine, but bends light and shapes motion. Gravitational lensing studies of the Coma cluster have confirmed this dark matter distribution. Light from background galaxies is distorted as it passes through the gravitational field of the cluster, allowing astronomers to infer the location and amount of mass present. These lensing maps show concentrations of mass where little visible matter exists, providing further proof that dark matter dominates the cluster's gravitational landscape. The galaxies within the Coma cluster also reveal a great deal about cosmic evolution. Most are old elliptical galaxies with very little star formation. They contain older stellar populations, and their smooth structures suggest a long history of gravitational interactions and mergers. This kind of environment, high density and frequent encounters, accelerates the transformation of galaxies. Gas is stripped, spiral arms are disrupted, galaxies merge into larger, more featureless forms. In this way, the Coma cluster serves as a time capsule of galactic aging. Still, not all galaxies in the cluster are dormant. Some show signs of recent star formation or active galactic nuclei. Radio observations have detected radio halos and relics, large-scale synchrotron emissions caused by accelerated electrons in the cluster's magnetic fields. These features hint at ongoing activity, possibly from recent mergers between galaxy groups within the cluster which generate shockwaves and turbulence. The Coma supercluster has become a calibration point for many cosmological models. Its detailed structure, well-measured redshifts, and wealth of multi-wavelength data data make it a benchmark for testing theories of cluster formation, galaxy evolution, and dark matter behavior. It also provides a reference for simulations such as the Millennium Simulation and Illustratus, which attempt to reproduce the growth of cosmic structure from the early universe to the present. The supercluster's location in the sky also makes it ideal for observation. It is positioned away from the plane of the Milky Way, so it suffers little from dust extinction or stellar crowding. This allows for deep optical and infrared imaging, precise spectroscopic surveys, and high-resolution X-ray and radio mapping. In many ways, it is the most accessible dense region of the cosmic web. Its proximity also means we can observe not just the cluster as a whole, but the individual galaxies in exquisite detail. Hubble Space Telescope images reveal intricate structures, stellar shells, dust lanes, and faint tidal tails, all remnants of the dynamical history that shaped each galaxy. In these features, we read the quiet evidence of cosmic evolution, etched into starlight and shadow. Another remarkable aspect of the Coma supercluster is its role in mapping the local velocity field. Peculiar velocity studies, measurements of galaxy motion relative to the general expansion, have shown that many galaxies in our vicinity experience a subtle drift toward the Coma region. While this motion is partially influenced by other mass concentrations such as the Shapley supercluster, the gravitational weight of Coma is undeniable. It is not simply a background structure. It exerts force, pulling gently across cosmic space, and yet despite its weight and brightness, the Coma supercluster is but one node in the greater web. Filaments extend from it like strands of a net, connecting to neighboring superclusters and flowing into the Laniakea basin. These connections are not visible in a single image. They emerge only when we map galaxies in 3 dimensions, turning flat constellations into living structures. The Coma supercluster reminds us that structure exists at every level, from individual stars and nebulae to galaxies. From groups and clusters to walls and webs, it is easy to become overwhelmed by scale, but in places like Coma we find a balance, a region large enough to challenge our understanding, yet close enough to study with care. In many ways, the Coma supercluster represents a kind of cosmological anchor. It is a place where theory meets observation, where models are tested against real data, and where mysteries such as dark matter are not only present but measurable. Its history, both as a scientific subject and as a physical structure, is deeply intertwined with the story of how we came to understand the universe's large-scale design.
Chapter 9. The Boötes Voids. In the constellation Boötes, nestled quietly within the northern sky, there is a region of space where the universe appears to disappear. Unlike the dense clusters and filaments we have explored so far, this place is remarkable not for what it contains but for what it lacks. It is called the Boötes Void, and it is one of the largest known cosmic voids ever discovered, a sphere of almost unimaginable emptiness, stretching across hundreds of millions of light-years. The Boötes Void was first identified in 1981, when a team of astronomers using redshift surveys began to notice a striking gap in the distribution of galaxies. They had expected to see a fairly uniform spread of galactic points across the sky, but in one region there were hardly any. What should have been dotted with galaxies was instead a dark, silent hole. This absence did not appear to be an observational error, nor a problem of dust obscuration. The region was clear, it was just empty. The void was found to have a diameter of roughly 330 million light-years. Its volume was enormous. For perspective, if the Milky Way sat at the center of this void, the nearest galaxy of comparable size would lie more than 150 million light-years away in every direction. At that scale, a journey across the void at the speed of light would take hundreds of millions of years, and one might not encounter a single luminous galaxy the entire time. Initially, this discovery was difficult to reconcile with the standard cosmological models. While voids are expected to exist, they are natural byproducts of structure formation. The Boötes Void appeared to be an outlier. Its size, shape, and relative isolation made it stand apart from the smaller, interconnected voids typically predicted by simulations. It was not a filaments gap or a pocket between walls. It was a sphere of stillness, a true region of cosmic isolation. To understand why this is so striking, we must return to the concept of large-scale structure. The universe is often compared to a sponge or a web. Clusters of galaxies form nodes, filaments connect them, and voids lie in between. But these voids are usually irregular in shape and modest in size. They are squeezed and stretched by the structures around them. The Boötes Void, however, appeared nearly spherical. Its symmetry was unsettling. It seemed too perfect, too empty, and too large to be a typical product of gravitational evolution. Over time, deeper surveys revealed that the void was not entirely empty. Faint galaxies, mostly dwarfs and irregulars, were eventually discovered within it. There are now an estimated 60 galaxies inside the Boötes Void, but given the size of the volume, that number is minuscule.
the average density of galaxies in the universe is thousands of times higher. This makes the Boötes Void a true underdense region, a nearly hollow pocket in the fabric of space-time. The causes of such a vast void are still debated. One explanation is that the Boötes Void formed naturally from the evolution of primordial density fluctuations. In the early universe, tiny variations in the distribution of matter acted as seeds for structure. High-density regions collapsed into galaxies and clusters, while low-density regions were left behind, expanding more rapidly. Over time, matter flowed away from the emptier regions and into the denser ones, leaving behind voids. The Boötes Void may be the result of several smaller voids merging together, a process known as void percolation. Just as clusters can merge to form superclusters, voids can combine into supervoids. This might explain its size and roundness. However, even under this model, the Boötes Void remains unusually large. Its rarity suggests that it is a significant statistical outlier, a structure that challenges the assumption that the universe is completely uniform on the largest scales. The void's influence is not only spatial, but also gravitational. Voids have mass, or rather they lack it, and that absence of mass affects the motion of nearby galaxies. Just as galaxies fall toward massive clusters, they also drift away from voids. This creates subtle but measurable flows in the cosmic velocity field. In the case of the Boötes Void, its presence likely influences the motion of surrounding structures, nudging clusters and filaments away from its boundary. Some studies have examined whether such voids could influence observations of the cosmic microwave background. Because voids are less dense, light traveling through them can be affected in unusual ways. This process, called the integrated Sachs-Wolf effect, occurs when photons pass through a changing gravitational potential. In theory, a void like Boötes could leave a slight temperature imprint on the cosmic microwave background. However, current data has not confirmed such an effect for this specific void. Still, the possibility remains a subject of ongoing research. Another avenue of interest is the distribution of dark matter within the void. Though the region is underdense in luminous matter, it is believed to contain dark matter, just in lower concentrations. Simulations suggest that even within voids, there are faint filaments of dark matter, forming a hidden web too subtle to detect with current instruments. These invisible threads may guide the motion of the few galaxies within the Boötes Void, and perhaps even influence the formation of new galaxies over cosmic timescales. Observing such voids also helps refine our understanding of galaxy bias, the relationship between dark matter and visible galaxies. Because galaxies are more likely to form in denser regions, the absence of galaxies in a void provides clues about the threshold conditions required for star formation and galactic evolution. By studying the galaxies that do exist within the Boötes Void, astronomers can explore how galaxies behave in isolation, cut off from the gravitational interactions, mergers, and environmental effects that shape galaxies in denser areas. These void galaxies often have unusual properties. Some are smaller and bluer than typical galaxies, suggesting ongoing star formation in a low-density environment. Others appear to be relics, older systems that have remained relatively unchanged. Because they are so isolated, they offer a unique laboratory for understanding how galaxies evolve without external disturbances. The Boötes Void also invites deeper philosophical questions. It is a reminder that the universe is not uniformly filled, that emptiness is not a flaw but a feature. For every cluster or filament, there is an equally essential gap, a silence that defines the shape of everything around it. The void is not absence, it is contrast. It is the canvas upon which structure appears. In cosmic terms, the Boötes Void is a region of stillness. Its galaxies are scattered thinly, their motions are slow and meandering. There are no dramatic mergers, no high-energy collisions, no sweeping arcs of starburst activity. There is only distance, a quiet, vast distance that stretches across space like a breath held for 100 million years. And yet that stillness is informative. It tells us how matter flows. It shows us where gravity is weak and where it is strong. It defines the edge of structure, marking the border between what has formed and what remains unformed. In this way, the Boötes Void is not just an anomaly. It is a crucial part of the cosmic architecture. As surveys grow more precise and instruments become more sensitive, new voids are being discovered across the sky. Some are larger than Boötes, some are closer, some are more irregular, but none have quite the same iconic status. The Boötes Void was the first to reveal the full scale of emptiness possible in the universe, and it remains one of the most profound. As we leave the Boötes Void behind, we now turn toward another kind of vastness, not an absence of galaxies, but an abundance of them, arranged in a filament so long and intricate, it weaves its way through the cosmic web like a highway of light.
Chapter 10. The Eridanus Supervoid. In the southern constellation of Eridanus, far beyond the reach of most naked-eye stars, there is a dark zone in the cosmic map, a region that absorbs attention, not because of what it contains, but because of what appears to be missing. This is the Eridanus Supervoid, an enormous underdense region in space that continues to puzzle cosmologists and observational astronomers alike. What makes the Eridanus Supervoid especially compelling
is that it overlaps with something even more mysterious, a large, unusually cold spot in the cosmic microwave background, known simply as the CMB cold spot. This cold spot, discovered by the Wilkinson Microwave Anisotropy Probe in 2004, and later confirmed by the Planck satellite, is not a normal feature. It is significantly colder than surrounding regions, and while some degree of temperature fluctuation is expected across the cosmic microwave background, this spot stands out. It is larger, colder, and harder to explain using standard models of early universe physics. Shortly after its discovery, cosmologists began searching for explanations. Could this cold spot be an artifact? Was it caused by instrumental error, galactic interference, or statistical coincidence? As the data was reanalyzed with different tools and deeper surveys, one correlation stood out. The location of the CMB cold spot aligned with a massive cosmic void in the direction of the Eridanus constellation. That void, now referred to as the Eridanus supervoid, quickly became a prime candidate for explaining the anomaly. The theory linking the two is grounded in gravitational physics. As photons from the early universe travel toward us, they pass through massive structures, clusters, filaments, and voids. In dense regions, they experience gravitational redshift as they climb out of potential wells. In underdense regions, the opposite can happen. Photons gain a small amount of energy entering a void, but if the void expands faster than expected while the photon is inside it, they may lose more energy exiting than they gained entering. This phenomenon is known as the integrated Sachs-Wolf effect. According to this model, the Eridanus supervoid, being especially vast and underdense, could have altered the energy of CMB photons that passed through it, resulting in a colder region of the sky as observed from Earth. It's an elegant explanation, and one that links cosmic structure directly to the earliest observable light in the universe. However, there is a complication. The magnitude of the temperature drop in the cold spot is too large to be fully explained by this void alone. Estimates suggest that even a void as large as Eridanus, which stretches across 1.8 billion light-years, making it one of the largest structures of its kind, cannot produce a cold spot as extreme as the one we observe. This discrepancy has led to two possibilities. The first is that the Eridanus supervoid is just one of several voids stacked along the same line of sight. Together, they might create a cumulative effect strong enough to produce the cold spot. The second is more speculative. Perhaps the cold spot reflects something more exotic, something beyond current physics. Some have suggested that the CMB cold spot could be a sign of non-standard inflationary fluctuations or even a bubble collision, a remnant signature from a hypothetical interaction with another universe during cosmic inflation. While these theories remain speculative, they reflect how a single observational anomaly can ripple through multiple areas of theoretical physics. Returning to the Eridanus supervoid itself, its properties are fascinating in their own right. Unlike the Boötes Void, which is roughly spherical, the Eridanus supervoid is shaped more like an elongated tube or flattened ellipsoid. Its irregular geometry complicates efforts to model its gravitational effects, but it also reveals how cosmic voids can vary in shape and depth, depending on the environment in which they formed. Within the supervoid, galaxies are not entirely absent, but they are far fewer and more isolated than in surrounding regions. Those that do exist often reside in small groups or faint filaments, with wide distances separating them. Many are dwarf galaxies or low-surface brightness systems, the kind that are difficult to detect in optical surveys. These galaxies tend to evolve more slowly, and their isolation provides a unique opportunity to study how structure and environment influence galaxy formation. Large cosmic voids like Eridanus are also important for constraining cosmological parameters. They act as sensitive tests for models of dark energy, especially when used in combination with void statistics across large surveys. Because voids expand differently from denser regions, tracking their growth can reveal how the universe's expansion rate has changed over time. In this sense, voids are not empty at all. They are rich in information. The Eridanus supervoid has been observed using multiple wavelengths, from optical and infrared surveys to radio observations and gravitational lensing maps. Each of these perspectives contributes something different. Infrared helps detect faint galaxies obscured by dust. Radio surveys track the neutral hydrogen gas between galaxies. Lensing observations can map the distribution of dark matter by detecting subtle distortions in the light of background galaxies. Lensing studies suggest that the Eridanus region is significantly underdense, though not entirely devoid of mass. The matter that does exist within the void is likely distributed in a diffuse manner, without the strong clustering typical of denser environments. This makes detection difficult, but the statistical weight of the void is still measurable in its gravitational effects. As with other large-scale structures, the Eridanus supervoid is not isolated. It is connected to the surrounding cosmic web, bounded by denser filaments that define its shape. These filaments act like the walls of a bubble, marking the edge where structure begins and emptiness ends. The void's boundary is especially sharp in some areas, indicating a significant contrast in matter density between the inside and outside regions. Cosmic voids do not simply sit motionless in space, they influence the motion of galaxies and gas around them.
Matter flows out of voids and into surrounding structures, a process known as void evacuation. This motion contributes to the overall velocity field of the universe. In the Eridanus region, galaxies near the edge of the void show coherent motion patterns, gently accelerating away from the center of the underdensity. These flows are subtle, but when measured across millions of galaxies, they provide critical constraints on models of gravitational behavior, especially in the context of dark energy. Different models predict different void dynamics, and observational data can help rule out or refine those predictions. The Eridanus supervoid is not the only massive void we have discovered, but its association with the CMB cold spot gives it a special status. It is a bridge between the very early universe and the modern cosmic web, a place where relic radiation meets evolving structure. It challenges both our observational techniques and our theoretical frameworks. It asks us to consider how small fluctuations at the beginning of time can lead to vast regions of emptiness today, and in doing so, it reminds us that space is not evenly filled. The universe breathes, it stretches and pulls, accumulates and evacuates, sculpts itself through gravity, and reveals its design not only in presence, but in profound silent absence.
Chapter 11. The Cosmic Web. When we look at the night sky, we see points of light scattered seemingly at random. Stars in our own galaxy form the constellations. Beyond them lie galaxies, faint and distant, shining as tiny islands across the deep sea of space. But as astronomers began to map these galaxies in 3 dimensions, a larger pattern began to emerge. A structure, a skeleton, a framework that stretches across the entire observable universe. This is what we now call the cosmic web. The cosmic web is the large-scale structure of the universe, an intricate network of galaxies, clusters, filaments and voids, all woven together by gravity and shaped by the evolution of matter since the Big Bang. It is not a flat surface or a grid, but a vast 3-dimensional arrangement of matter, spanning billions of light-years in every direction. It connects the smallest galaxies to the largest superclusters, and it holds within it the shape of cosmic history itself. The origin of the cosmic web lies in the early universe, when the cosmos was filled with a nearly uniform plasma of hydrogen and helium. Small fluctuations in density, tiny imprints left in the cosmic microwave background, acted as seeds for future structure. Over billions of years, these slight overdensities attracted more matter through gravity, eventually collapsing into stars, galaxies, and clusters. As matter flowed into these regions, it also left behind emptier spaces, voids where galaxies would become rare. This push and pull over time created the filamentary structure we now observe. The term web is not metaphorical. When mapped using large redshift surveys, the universe truly appears to resemble a vast, interconnected web. Galaxies are not distributed evenly. They form long threads and walls. At the intersections of these filaments are dense clusters, where thousands of galaxies gather. Between these nodes lie enormous voids, regions hundreds of millions of light-years wide, nearly empty of visible matter. One of the earliest projects to reveal this structure was the CFA Redshift Survey, which produced wedge-shaped maps showing how galaxies were distributed with distance. Instead of seeing a smooth cloud of points, astronomers observed large-scale patterns, walls, filaments, and gaps. Later surveys, including the Sloan Digital Sky Survey and 2DF Galaxy Redshift Survey, provided even more detailed maps. These showed that the cosmic web is not just local, it extends across the entire observable universe. The web is primarily shaped by dark matter, an invisible form of mass that does not emit, absorb, or reflect light. Dark matter makes up about 85% of all matter in the universe. It interacts through gravity, and it serves as the scaffolding upon which visible matter gathers. Galaxies form along the filaments of dark matter, and their distribution follows its contours. Even though we cannot see the dark matter directly, we can trace its presence through gravitational lensing, galaxy motions, and numerical simulations. These simulations, such as the Millennium Simulation and Illustris project, model the evolution of structure in the universe using billions of particles. Starting with the initial conditions observed in the cosmic microwave background, they evolve these particles forward in time using the laws of gravity and fluid dynamics. The result is a virtual universe, and it looks remarkably like what we observe. Filaments form, clusters grow, voids expand, the cosmic web emerges, woven naturally from the interaction of mass and time. What is striking about the web is its scale invariance. Its structure looks similar at different magnifications. Whether you zoom in on a filament a few 100 million light-years long, or pull back to view the global arrangement of superclusters, the pattern persists. This self-similarity hints at deeper mathematical principles, possibly rooted in the physics of the early universe and the influence of dark energy. Each component of the cosmic web serves a different role. Nodes or clusters are dense, gravitationally bound collections of galaxies. They are the most massive collapse structures in the universe, and they often lie at the intersections of filaments. Filaments are elongated chains of galaxies and dark matter connecting clusters across vast distances. They are the highways of the universe, along which galaxies and gas flow. Walls are sheets of galaxies, often made of multiple filaments, and they can span hundreds of millions of light-years in length. Finally, voids are the large empty spaces between these structures, the silent background that defines the web's contrast. Galaxies are not stationary within the web. They move. They drift slowly along filaments toward denser nodes. This motion, known as cosmic flow, is shaped by the underlying gravitational potential. Matter flows out of voids and into filaments. Gas streams toward clusters, feeding star formation and fueling the growth of galaxies. The cosmic web is not frozen in place. It is dynamic, evolving, and responsive. Studies of the web have shown that a galaxy's location within it can influence its properties. Galaxies in dense nodes tend to be older, larger, and more elliptical, while galaxies in filaments are more likely to be star-forming spirals. In the sparsest environments, near the edges of voids, galaxies tend to be small, blue, and less evolved. This environmental effect is known as large-scale bias, and it helps explain the diversity of galaxies we observe. The cosmic web also plays a key role in the formation of cosmic magnetic fields. As gas flows along filaments, it can generate turbulence and compress magnetic fields, possibly contributing to the widespread magnetization of the intergalactic medium. These magnetic fields are difficult to detect directly, but their signatures are observed in radio emissions and in the alignment of cosmic rays. In recent years, new methods have allowed astronomers to probe the cosmic web more deeply. One approach involves observing the Lyman alpha forest, a series of absorption lines in the spectra of distant quasars. These lines are caused by clouds of hydrogen gas in intergalactic space. By analyzing their distribution, researchers can reconstruct the density of matter along the line of sight, effectively mapping the filaments between galaxies. Another method uses Sonuev-Zeldovich measurements, which detect changes in the cosmic microwave background caused by hot electrons in galaxy clusters and filaments. This technique allows astronomers to study the gas that flows between galaxies, the intergalactic medium that makes up most of the normal matter in the universe. Yet, despite all of this, we have still only glimpsed a fraction of the cosmic web. Much of it remains invisible, not because it is not there, but because it is faint. The filaments connecting galaxy clusters are tenuous, filled with diffuse gas and dark matter that are difficult to detect with current instruments. But as our technology improves, so too does our ability to trace these cosmic threads. Understanding the cosmic web is essential for many areas of astrophysics and cosmology. It is the context for galaxy formation, the pathway for matter flow, and the map against which gravitational dynamics play out. It also serves as a powerful test of cosmological models. Different theories of dark energy and modified gravity make different predictions about how the web evolves. By comparing simulations to observations, we can test these theories in a universe that acts as its own laboratory. The cosmic web is not only a scientific structure, it is also a poetic one. It transforms our view of the universe from a scatter of galaxies into a meaningful pattern. It reveals the deep order behind apparent chaos. It connects every galaxy to every other, not in isolation, but in relationship, a grand network of presence shaped by time, gravity, and space. And yet, for all its vastness, the web is still young. In the distant future, dark energy will continue to drive the universe's expansion. Galaxies will move farther apart, the filaments will thin. Eventually, most structures will drift beyond the cosmic horizon, rendering them invisible to any observers that remain. The cosmic web will fade, but for now, it holds the memory of creation and the map of what the universe has become.
Chapter 12. The KBC Voids. There is a quiet controversy at the heart of cosmology, a debate that rests not on distant galaxies or ancient light, but on where we ourselves are located in the universe. For many decades, the cosmological principle has guided our thinking, the idea that on the largest scales, the universe is both homogeneous and isotropic. It should look the same in every direction, and every observer, no matter where they are, should see roughly the same large-scale structure. But what if that's not entirely true? What if we live inside a giant underdensity, a void, and that void is quietly affecting everything we observe? This idea, though provocative, is not science fiction. It is based on real observations, real measurements, and it has a name, the KBC Void, named after the three researchers, Keenan, Barger, and Cowie, who published a paper in 2013 suggesting that the local universe appears to be less dense in galaxies and matter than regions farther away. According to their data, when we measure the number of galaxies and the brightness of the extragalactic background light in regions within about 300 million light-years, we find that the density is significantly lower than in shells farther out. This means that statistically, we may be sitting inside a large underdense region.
not completely empty, but measurably less populated by galaxies in mass than the cosmic average. The implications of this are profound. First, such a void could help explain some of the persistent tension in modern cosmology, specifically the discrepancy between local and early universe measurements of the Hubble constant. When astronomers measure how fast the universe is expanding using nearby galaxies and Type 1I supernovae, they arrive at a value for the Hubble constant that is higher than what is calculated from the cosmic microwave background and early universe models. This mismatch is known as the Hubble tension, and it has puzzled researchers for years. If we live in a large underdensity, then the galaxies around us would be gravitationally influenced by a different local environment. They would be receding from us faster than expected, not because the entire universe is expanding faster, but because we are measuring from within a region where gravity is slightly weaker and the expansion is locally accelerated. This would naturally lead to a higher observed Hubble constant in the local universe without requiring exotic new physics. The KBC void is estimated to be roughly 1 to 1.5 billion light-years in diameter, with our position near its center. This would make it one of the largest voids ever proposed, larger even than the Boötes or Eridanus supervoids. However, it is not entirely empty. Rather, it is a region of low-density contrast, underdense but not to the point of being a complete vacuum. Galaxies still exist within it, clusters still form, but the average matter density is lower than the cosmic mean. One of the key challenges in studying the KBC void is observational uncertainty. Mapping the large-scale distribution of galaxies is not easy, especially in directions obscured by the plane of the Milky Way, or in regions that have not been deeply surveyed. It is also difficult to distinguish between a real large-scale underdensity and statistical fluctuations in galaxy clustering. That's why researchers use a variety of independent measurements, including galaxy counts, supernova surveys, gravitational lensing, and even the integrated Sachs-Wolf effect to test whether the KBC void is truly present. Some models suggest that if such a void exists, it must be spherically symmetric and centered very close to our own position. If we were significantly off-center, we would see large anisotropies in the cosmic microwave background and in the redshift distribution of galaxies. So far, the data does not show such asymmetries, which strengthens the case that if a void exists, we are near its middle, a statistically unlikely but not impossible scenario. Critics of the KBC void hypothesis point out that it requires a rare configuration and that other explanations for the Hubble tension may be more plausible, including modified gravity, early dark energy, or unrecognized systematic errors in data collection. However, the void model remains attractive because it does not invoke new particles or forces. It is based on known physics applied to an inhomogeneous distribution of matter. The idea that our cosmic neighborhood may be special in this way is somewhat uncomfortable. For centuries, astronomy has moved us away from the idea that Earth or humanity occupies a central position in the universe, but the existence of a local void does not imply cosmic privilege. It may simply be the result of statistical chance, just as some regions of space contain large clusters and others contain none. Over a large enough volume, the universe may still be homogeneous, even if smaller regions like ours deviate from that average. To explore this further, astronomers have turned to gravitational lensing maps, which trace the total matter distribution, including dark matter, in the universe. If the KBC void is real, it should appear in lensing surveys as a region of reduced lensing strength, indicating less mass. Preliminary data has shown hints of this underdensity, but the resolution and depth of current lensing surveys make it difficult to confirm with high precision. Future missions, such as the Euclid Space Telescope and the Vera C. Rubin Observatory, may provide the necessary data to confirm or refute the void's presence. In addition to gravitational lensing, researchers study Type 1A supernovae in the local and distant universe. Because these stellar explosions act as standard candles, objects of known brightness, they allow astronomers to measure distance and expansion rate with high accuracy. By comparing supernova data inside and outside the proposed void, scientists can test whether the expansion appears faster in our region than in denser areas farther away. So far, the results have been mixed, with some surveys suggesting a slight local acceleration and others showing more uniform expansion. Another approach is to examine the kinematic Sonyev-Zeldovich effect, which occurs when the motion of galaxy clusters relative to the cosmic microwave background affects the observed temperature of the CMB. If we live in a large void, then nearby clusters may have peculiar velocities directed outward as matter flows away from the underdensity towards surrounding denser regions. Detecting these motion patterns can provide indirect evidence for or against the void model. What remains remarkable is that the question is still open. The idea that our region of the universe might be slightly different from the cosmic average forces us to reconsider how we interpret cosmological data. It is a reminder that observations are never made in a vacuum. They are always shaped by the position and context of the observer. If the KBC void exists, then it would affect not only our measurements of cosmic expansion, but also our models of structure formation and dark energy. Cosmic voids in general are still not fully understood. They are complex, evolving regions that interact with the surrounding web of matter. Some may be the remnants of large-scale fluctuations from the early universe. Others may result from nonlinear structure evolution and gravitational dynamics. Understanding how voids form, grow, and connect to the larger cosmic architecture is one of the ongoing challenges of modern astrophysics. In this context, the KBC void is not just a curiosity, it is a critical test case. It lies at the intersection of local observations and global models. It may help explain tensions in cosmological data, or it may point to deeper issues in how we model the universe. Either way, its investigation leads us toward more precise, more careful science. And whether or not the KBC void is ultimately confirmed, its story reminds us that the universe is not uniform in its details. Even as it appears to be smooth and balanced at the largest scales, its texture is varied. Some regions are filled with galaxies, others are quieter, more diffuse, more subtle, and somewhere in the midst of this quiet structure we find ourselves.
Chapter 13. The Laniakea Supercluster. In the vast architecture of the cosmos, our galaxy, the Milky Way, is only one among hundreds of billions. For most of human history, we believed it to be the center of the universe. But as our telescopes grew stronger, we saw that it was just a spiral drifting among many others, bound into a small group, orbiting with neighbors, and orbiting still larger gravitational structures. Today, we know that the Milky Way is part of a local group of galaxies, a small cluster that includes Andromeda, the Triangulum Galaxy, and dozens of smaller companions. This group, in turn, is located within a dense region of space called the Virgo supercluster, home to thousands of galaxies. But even that is only part of a much larger, newly defined structure, a region that connects hundreds of superclusters and encompasses over 100,000 galaxies across more than 500 million light-years. This is the Laniakea supercluster, and it may be one of the most significant discoveries in our understanding of the large-scale structure of the universe. The name Laniakea comes from the Hawaiian language, meaning immense heaven. It was chosen by the astronomers who mapped this region using galaxy motion data, an acknowledgement of both the cultural legacy of celestial navigation in Hawaii and the immense scale of what was being described. The Laniakea supercluster redefines our understanding of where we live in the universe, not based just on where galaxies are located, but on how they move through space under the influence of gravity. The discovery of Laniakea was made possible through peculiar velocity mapping. Unlike simple redshift surveys, which only measure how fast galaxies are moving away due to cosmic expansion, peculiar velocity studies look at how galaxies deviate from that expansion. These deviations are caused by gravitational interactions with other massive structures. In short, galaxies fall toward gravity wells. By analyzing these flows, astronomers can reconstruct the gravitational landscape of the universe, and it was through this method that Laniakea emerged. The key insight was that many galaxies previously thought to belong to separate superclusters were actually converging toward a single gravitational basin, a point of attraction that appears to guide the motion of galaxies across hundreds of millions of light-years. This point is associated with a region known as the Great Attractor, a mysterious mass concentration that has long puzzled astronomers due to its gravitational influence on local galaxy flows. Laniakea encompasses the Great Attractor, along with the Virgo supercluster and other previously disconnected structures, uniting them into a single coherent flow zone. The boundary of Laniakea is defined not by a physical edge or wall of galaxies, but by a watershed of motion. Just as rivers on Earth flow toward particular oceans based on the shape of terrain, galaxies within Laniakea flow toward a common center of gravity. Those outside this gravitational watershed flow elsewhere. This concept is a radical shift in cosmic mapping, moving from static position-based definitions to dynamic, motion-based structure. The total mass of Laniakea is estimated to be around 10^19 solar masses, and its diameter spans over 500 million light-years. Within it are many recognizable components: the Virgo supercluster, the Hydra Centaurus supercluster, and the Norma cluster, the core region associated with the Great Attractor. These massive clusters serve as nodes within the supercluster, drawing in galaxies and gas from the surrounding filamentary structure. The role of the Great Attractor within Laniakea is still not fully understood. It lies in a region of the sky obscured by the plane of the Milky Way, making observations difficult. However, its gravitational influence is evident in the peculiar velocities of galaxies across the sky. Even our own galaxy is moving toward it at a speed of over 600 kilometers per second, a motion superimposed on the general expansion of the universe. This drift, while slow on human timescales, is significant over cosmic distances.
Understanding Laniakea also helps refine our models of the cosmic web. Superclusters like Laniakea are the largest known coherent structures in the universe, yet they are not gravitationally bound in the long term. Dark energy, the mysterious force driving cosmic acceleration, will eventually pull these structures apart. Laniakea is bound now, but in the far future its galaxies will drift away from each other, each becoming isolated islands in an ever-quieting universe. One of the more fascinating aspects of Laniakea is its relation to other nearby gravitational structures. Outside its boundary lies another immense supercluster called Perseus Pisces, and farther still the Shapley supercluster, an enormous concentration of mass even more distant than the Great Attractor. These structures are not randomly placed. They are all connected by vast filaments of dark matter and galaxies, threaded together like beads on a string, stretching across billions of light-years. The Laniakea supercluster is not an isolated unit, but one element of this interconnected cosmic tapestry. It is shaped by its neighboring voids and filaments, by the flow of matter across space, and by the subtle influence of dark energy in the background. Its structure is not permanent, but a temporary expression of balance, the result of countless interactions among galaxies, gravity, and time. To visualize Laniakea, astronomers have used data from galaxy redshifts, X-ray maps of clusters, and velocity field reconstructions from surveys like cosmic flows. Three-dimensional models show streamlines, paths that galaxies follow over time, converging toward the gravitational basin near the Norma cluster. These models resemble a spiderweb of light, twisting and folding through space, each line a silent journey shaped by unseen mass. For our galaxy, the Milky Way, Laniakea represents the dynamic context in which it exists. We are not drifting randomly in space. We are moving along a river of gravity, drawn toward larger scales, curved by the invisible forces that hold the structure of the universe together. And we are not alone. All nearby galaxies are flowing with us, each on its own path, but all drawn toward the same deep gravity well. This shared motion gives rise to a sense of cosmic unity. In a universe that is otherwise expanding, these regional flows are reminders that gravity still shapes local environments. Galaxies are not just being pulled apart, they are also falling inward, clustering, colliding, and merging. Laniakea, like all superclusters, is a place where this tension plays out, expansion on one hand, gravitational binding on the other. It's important to note that Laniakea is not gravitationally bound in the strictest sense. Its scale is too large. Dark energy dominates at these distances. Over billions of years, the galaxies within it will lose their ability to remain connected. But for now, while the flow continues, it is a meaningful structure, a snapshot in time, a shape drawn by motion. The discovery of Laniakea marked a turning point in how we define cosmic structures. It challenged the older idea of naming superclusters by static shape or apparent location. Instead, it introduced a definition based on gravitational influence and velocity flow. This dynamic definition may apply to future mappings of the universe, as we move from passive observation to active modeling of cosmic dynamics. And perhaps more than anything, Laniakea reminds us that scale is relative. What once seemed large, the Milky Way, the Virgo cluster, is now seen as a small part of something much greater. Each step back reveals a broader pattern. Each new survey adds detail to the vast design. And yet that pattern is not random. It is shaped by rules, by the laws of gravity, thermodynamics, and cosmic expansion, playing out over unimaginable distances and timescales.
Chapter 14. The Shapley Supercluster. In the southern sky, far beyond the reach of our local supercluster, lies one of the most massive known structures in the observable universe. It is not subtle, it is not hidden, it does not lurk in the shadows of observational uncertainty. Instead, it looms. Its gravitational weight stretches across hundreds of millions of light-years. It bends the flow of galaxies. It may even be affecting the motion of our own local group, despite lying hundreds of millions of light-years away. This structure is known as the Shapley supercluster, and its influence is as extraordinary as its scale. Named after the astronomer Harlow Shapley, who first noted the unusual concentration of galaxies in this region in the early 20th century, the Shapley supercluster lies in the constellation Centaurus. It is centered roughly 650 million light-years from Earth and spans an estimated 600 million light-years across. Unlike many superclusters that are more diffuse or modest in mass, Shapley is densely packed with galaxy clusters, some of the most massive ever discovered. These clusters are not isolated, they are gravitationally interacting, forming a connected lattice of mass that curves the local geometry of space. One of the most striking features of the Shapley supercluster is the concentration of rich Abell galaxy clusters. Abell 3558, Abell 3562, and several others dominate the core region, surrounded by a swarm of smaller groupings and extended filaments. The cumulative mass of the entire structure is thought to be more than 10 quadrillion solar masses, with some estimates pushing even higher, depending on how far the structure extends. This mass is not merely theoretical, it reveals itself through its effects on galaxy motion, X-ray emissions from hot gas, and gravitational lensing. The Shapley supercluster is sometimes referred to as the Shapley concentration, to emphasize the tight grouping of matter within its boundaries. This tightness is key. Unlike the more sprawling configurations of superclusters like Laniakea, Shapley is dense and active. Its core contains some of the hottest, brightest intracluster gas ever observed. X-ray maps from telescopes like XMM Newton and Chandra reveal searing clouds of ionized plasma, heated by gravitational compression and frequent galactic mergers. As galaxies and clusters fall toward the gravitational center of the Shapley supercluster, they accelerate, they compress, they interact violently. The result is a region where star formation rates fluctuate, where active galactic nuclei flare, and where gas is stripped, shocked, and recycled. This activity makes Shapley not only massive, but dynamically young, a structure still assembling, still evolving. One of the most significant cosmological questions regarding the Shapley supercluster is whether it contributes to the peculiar velocity of our own galaxy. For decades, astronomers have puzzled over why the Milky Way, and indeed our entire local group, is moving at over 600 kilometers per second relative to the cosmic microwave background. This motion, known as the dipole anisotropy, requires explanation. Some of it can be attributed to local structures like the Virgo cluster or the Great Attractor, but calculations suggest these may not fully account for the observed speed and direction. The Shapley supercluster, due to its sheer mass and relatively close proximity, has been proposed as a key contributor. Even though it lies far beyond the Great Attractor, its gravitational influence may extend all the way to our region. This idea has been tested using galaxy flow models, which simulate the combined gravitational effects of known structures. These models indicate that the motion of the local group is not aimed directly at the Great Attractor, but rather veers slightly, possibly aligning more closely with the mass center of Shapley. Further support for this idea comes from studies of dipole repellers and attractors, concepts introduced to describe the balance of forces in the universe's large-scale structure. According to this model, the motion of our galaxy can be understood as the result of a pull from the Shapley supercluster and a push from a nearby void, the dipole repeller. This dual-force framework provides a more complete explanation for cosmic flows and places Shapley at the far edge of our observable influence zone. Beyond its dynamical effects, the Shapley supercluster also serves as a cosmic laboratory for understanding the evolution of large structures. Its dense core, filled with mature elliptical galaxies, shows signs of environmental quenching, a process in which star formation is suppressed due to the high-pressure, high-temperature environment. Gas-rich spiral galaxies entering the supercluster often lose their gas quickly, transforming into red, passive systems. This evolutionary trend helps scientists trace the pathway of galaxy transformation as they fall deeper into massive cosmic structures. Another important feature of the Shapley supercluster is its alignment with surrounding filaments. It is not isolated, but rather connected by long strands of galaxies to other nearby clusters. This alignment suggests a hierarchical assembly process where filaments feed mass into central supercluster regions, building them up over time. This process, called anisotropic infall, is observed in simulations of structure formation and is supported by the real spatial configuration of galaxies near Shapley. Gravitational lensing has provided additional confirmation of the supercluster's mass. Weak lensing studies, which detect the subtle distortion of background galaxies due to foreground mass, reveal an extended mass distribution that agrees with X-ray and redshift data. This convergence of methods strengthens the conclusion that Shapley is not only vast, but among the most massive overdensities in the nearby universe. The intense mass concentration of the Shapley supercluster raises further questions about cosmic variance. According to standard cosmology, the distribution of matter on large scales should be fairly smooth and statistically predictable, yet Shapley's density appears to exceed expected thresholds. This leads some researchers to explore whether structures like Shapley represent rare statistical outliers, or whether they point to subtle problems in our models of initial density fluctuations. Shapley's richness also makes it a target for studying galaxy cluster mergers. Several clusters within its bounds are in the process of colliding, massive events that release enormous energy into the surrounding gas. Shock fronts and turbulence are generated, creating radio halos and relics that trace the dynamic past of these regions. By observing these features across multiple wavelengths, optical, X-ray, and radio, astronomers can reconstruct the history of interaction and merger within the supercluster. Despite its scale, the Shapley supercluster is still part of the broader cosmic web. It exists within a lattice of filaments, walls, and voids. It is shaped by the expansion of the universe, as well as by the gravitational pull of its own components, and it will not remain as it is. In time, dark energy will stretch space so rapidly that gravitational interactions across these scales will weaken. Superclusters like Shapley may never fully collapse into bound structures. They may instead fragment and drift apart, leaving behind fossil imprints of their former shape. The Shapley supercluster, then, represents a moment in cosmic time. It is a temporary convergence of mass, light, and gravity, a portrait of what the universe can become. When enough matter gathers in one region, its influence is felt far beyond its core. Its structure is rich with clues, and its presence reminds us that the universe still has surprises left to reveal.
Chapter 15. The Boötes Voids. When we gaze into the night sky, We often marvel at the abundance of stars, the richness of galaxies, and the dense patterns traced by the cosmic web. The universe appears full, luminous, and ever-expanding. But amid this brilliance, there are places where the light goes silent, regions not crowded with galaxies or clusters, but almost entirely empty. These spaces are not small, they are vast, stretching across hundreds of millions of light-years, and perhaps the most haunting of them all is the Boötes Void, a region so large and so underpopulated that it has been called one of the greatest mysteries of large-scale cosmic structure. Located in the direction of the constellation Boötes, this void was first discovered in 1981 during a redshift survey led by Robert Kirshner and his colleagues. As the team mapped galaxy positions in 3 dimensions, they began to notice something strange. A certain region of the sky contained far fewer galaxies than expected, not a thin patch, not a gap between clusters, but a yawning absence. Over time, as more data was gathered and more redshifts were measured, the true scope of this void became clear. The Boötes Void spans nearly 330 million light-years in diameter, making it one of the largest known voids in the observable universe. To understand how remarkable this is, one must consider the average distribution of galaxies across the sky. In most directions, galaxies are fairly well spaced. The large-scale structure of the universe resembles a cosmic sponge or a web, with filaments, nodes and bubbles, but the Boötes Void contains fewer than 100 galaxies across a volume of space where thousands would normally be expected. It is not simply a less dense region, it is, in comparison to its surroundings, a desert. The emptiness of the Boötes Void is not just a curiosity, it is a challenge to our models of structure formation. According to standard cosmological theory, large voids can form from regions of lower than average density in the early universe. These underdensities expand faster than their surroundings, as gravitational attraction pulls more matter into denser regions and away from the emptier ones. Over billions of years, this process evacuates matter from the voids, leaving behind cold, sparse regions dominated by dark energy and dark matter. But the Boötes Void is so large and so sharply defined that it raises important questions about how such an extreme structure could have evolved. One explanation is that the Boötes Void is not a single coherent structure, but a superposition of multiple smaller voids that have merged together. This idea, sometimes called the void-in-void scenario, suggests that over time, smaller underdense regions can coalesce into larger ones as matter continues to flow outward. Simulations of large-scale structure have shown that this process is plausible, but the Boötes Void still lies at the extreme end of these models, near the edge of what is considered likely based on initial conditions. Interestingly, the galaxies that do exist inside the Boötes Void are not entirely inactive. Some are irregular or low-mass dwarf galaxies, and others show signs of ongoing star formation. In such isolation, these galaxies provide unique laboratories for understanding galactic evolution outside of dense environments. Without frequent interactions or gravitational harassment from neighbors, these void galaxies may evolve differently from those in clusters or filaments. Some astronomers study them to explore whether internal processes alone can drive star formation, without external triggers. Because the Boötes Void is so massive, it also influences the gravitational environment around it. Galaxies near the edge of the void experience a kind of gravitational imbalance. They are not being pulled inward, but instead feel a gentle outward flow, a gravitational repulsion created by the lack of mass in the center. This flow affects the peculiar velocities of nearby galaxies and can be mapped to study the shape and extent of the void. In this sense, the void is not just an absence of matter, it is an active feature in the gravitational fabric of the cosmos. Another fascinating aspect of the Boötes Void is how little it was expected. Before its discovery, redshift surveys had not reached far enough or deep enough to detect such enormous structures. When it was first mapped, many astronomers were skeptical, unsure whether the data might be incomplete or misinterpreted. But repeated surveys confirmed the finding, and the void's existence became a key data point in support of the idea that the universe contains not just filaments and clusters, but also immense persistent vacuums. These voids, like the Boötes, Eridanus and KBC voids, remind us that structure in the universe is not only built through addition and gathering, but also through absence and subtraction. Voids occupy the majority of cosmic volume, even though they contain a small fraction of the mass. In that sense, they are the background upon which the galaxies are painted, the negative space in the grand composition of the universe. From a cosmological standpoint, voids are valuable tools. They provide cleaner environments for testing theories about dark energy, modified gravity, and structure growth. Since these regions are relatively simple, lacking the chaotic interactions found in clusters, they allow for more straightforward comparisons between theory and observation.
some researchers have proposed using the shapes of voids to constrain the equation of state of dark energy. Others have looked at how voids evolve over time in different cosmological models to distinguish between competing theories of gravity. The Boötes Void, in particular, has been modeled in high-resolution N-body simulations. These simulations replicate the evolution of matter from the early universe to the present, allowing researchers to ask how often voids of this size should appear. While rare, voids like Boötes can be reproduced in some scenarios, especially those with slightly higher initial fluctuations or warmer dark matter models. Still, its presence near our observational range raises interesting statistical questions. Are we in a part of the universe that just happens to contain more extreme structures, or are our theories still missing something? Some cosmologists have even considered whether large voids like Boötes could create observable effects in the cosmic microwave background. Through the integrated Sachs-Wolf effect, photons from the CMB passing through large voids can gain or lose energy, depending on how the gravitational potential changes during their journey. If the Boötes Void is aligned with CMB anomalies, it could help explain features like the cold spot, though current data is not conclusive. In visualizations of the universe's large-scale structure, the Boötes Void appears as a sphere of near silence. It is surrounded on all sides by filaments and superclusters, forming a kind of cosmic shell. The galaxies on the perimeter are denser, brighter, and more dynamic, while the center remains dim. Some renderings show the void as a great dark orb in space, not because it is inherently black, but because so few galaxies within it emit visible light. What lies in the center of such a void? The answer is almost nothing. Sparse gas, low-temperature background radiation, and dark matter spread so thin it might as well be transparent. And yet, even in this emptiness, there is motion, there is structure, there is meaning. The Boötes Void is not a true nothingness. It is a place where the universe has expanded a little faster, where gravity has lost the competition, where silence has temporarily won. For those who study cosmology, voids like Boötes are not just features to be catalogued, but puzzles to be solved. They offer a window into the balance of forces that shape the universe, the push of expansion, the pull of gravity, the ripples of quantum fluctuations, and the role of invisible dark matter. Each void is a relic of that cosmic contest, a fossil imprint of the universe's earliest decisions. Some even see a kind of poetic symmetry in the Boötes Void. As galaxies form stars, and stars form elements, and elements form life, it is easy to imagine that only dense places matter. But without the quiet spaces, the loud ones have no contrast. Without the dark, the light is harder to see. The Boötes Void is a monument to that contrast, a reminder that even absence has a shape, a role and a story. As the universe continues to expand, the Boötes Void will grow even larger. Galaxies at its edge will continue to move away from each other, and the few galaxies within it may become ever more isolated. Over cosmic time, the void may stretch so far that even light from its interior can no longer reach the surrounding sky. It will become quieter, darker, and emptier, a slow evaporation of structure, and yet for now, it stands as one of the most dramatic features of our observable cosmos. It is not a destination, not a place anyone will ever reach, but it is a presence, a gravitational reality that shapes the movement of galaxies and the thinking of scientists. In that sense, the Boötes Void is not just empty, it is full of consequence.
Chapter 16. The Sloan Great Wall. There are moments in the history of science when a discovery does not just add a new piece to the puzzle, it changes the shape of the puzzle itself. When astronomers mapped the Sloan Great Wall in the early 2000s, that's exactly what happened. It was not merely another filament in the growing map of the cosmic web. It was a structure so vast, so coherent, and so staggeringly long that it forced cosmologists to reconsider what limits, if any, should exist on the size of structures in the universe. It was a reminder that space does not simply contain galaxies, it arranges them, strings them, and sometimes stretches them into walls of unimaginable scale. The Sloan Great Wall was discovered in 2003, using data from the Sloan Digital Sky Survey, a groundbreaking project that aimed to create a three-dimensional map of the nearby universe by measuring the redshifts and positions of millions of galaxies. As the survey expanded its coverage and began to trace the structure of galaxy distributions on large scales, a continuous chain of galaxies, clusters, and filaments appeared to stretch across the sky, connecting regions that were hundreds of millions of light-years apart. Further analysis confirmed that these structures were not just projected on the sky, but were physically connected in three-dimensional space. This formation, now known as the Sloan Great Wall, measures more than 1.37 billion light-years across, one of the longest coherent features ever observed in the cosmos. To appreciate the scale of this structure, one must place it in context. The Milky Way galaxy is around 100,000 light-years in diameter. The local group, which includes our galaxy and its nearest neighbors, spans several million light-years. Even our larger home, the Laniakea supercluster, is about 500 million light-years across. The Sloan Great Wall surpasses all of these. It is not simply a supercluster, it is a chain of them, a spine in the cosmic skeleton, running nearly 1/10 the length of the observable universe. The Sloan Great Wall is not a single uniform mass of galaxies. Instead, it consists of multiple dense regions, superclusters, galaxy groups, and filaments, all gravitationally connected and moving within the same large-scale flow. Among its components are well-known groupings like the Sloan cluster and the Sloan extension, as well as several dense filaments, whose velocities suggest that they are not just aligned by chance, but linked by shared gravitational history. These features together form a wall-like distribution of galaxies, a curtain drawn across the sky in deep space. Structures like the Sloan Great Wall emerge naturally in simulations of large-scale structure formation. In the early universe, quantum fluctuations in the density of matter seeded the formation of stars, galaxies, and eventually clusters. As gravity pulled matter together, overdense regions grew while underdense regions expanded more rapidly. This gravitational clustering created a cosmic web, a network of nodes, filaments, and voids that mirrors the sponge-like structure we observe today. But the Sloan Great Wall stands out even among these features. Its sheer length and coherence make it a statistical anomaly, a structure that pushes the boundaries of what is expected in a universe governed by the standard model of cosmology. This statistical tension has sparked debate. Is the Sloan Great Wall an extreme but still natural outcome of the lambda-cold dark matter lens CDM model, or does it suggest that our current understanding of the universe's structure is incomplete? Some simulations can produce similar large-scale features, but only under specific initial conditions or by accepting that such structures are rare flukes, the result of random clustering on improbable scales. Others suggest that such vast alignments may point towards subtle new physics or require a rethinking of the initial density perturbations in the early universe. Regardless of its theoretical implications, the observational reality of the Sloan Great Wall remains clear. Surveys have confirmed its continuity, and independent redshift measurements have validated its scale. The wall spans roughly 1/15 of the observable universe's radius and contains thousands of galaxies, hundreds of galaxy clusters, and massive quantities of dark matter and hot intergalactic gas. It is a gravitationally influential feature, one that likely impacts the motion of nearby clusters and shapes the local flows of galaxy groups around it. The structure also highlights the importance of perspective in cosmic mapping. Before the Sloan Digital Sky Survey, we had no idea that such a formation existed in that region of space. It was not hidden, it was simply too large to recognize in fragmented datasets. Only by assembling a wide, deep, and continuous map were astronomers able to see the shape emerge. It was as if a mosaic of night sky had suddenly snapped into place, revealing a portrait that had always been there but had never been seen in full. One of the most intriguing aspects of the Sloan Great Wall is how it challenges our psychological intuitions. Human beings are accustomed to dealing with scales we can see, touch, or at least imagine. Kilometers, continents, planets, even galaxies, once you become familiar with their structure, can be mentally represented. But the Sloan Great Wall exists on a scale that resists mental grasp. It is 1 billion light-years long. Light, moving at the fastest speed possible in the universe, would take more than 1 billion years to traverse its length. And yet, from our vantage point, we see it not as a line, but as a silent arc of data points, as a gravitational feature that shapes the sky without making a sound. Its existence prompts other, deeper questions. What is the largest structure the universe can support? Is there a limit beyond which even gravity cannot organize matter into coherent forms? And if the Sloan Great Wall does not exceed that limit, how close is it? Some cosmologists have explored this question through the correlation length, a statistical measure of how galaxy distributions deviate from randomness. According to some calculations, structures larger than about 300 million light-years should be increasingly rare, yet structures like the Sloan Great Wall, and others we will explore, exceed this range. In 2011, a study using the SDSS-DR7 dataset found that the Sloan Great Wall might not be a single structure after all, but rather a projection of multiple aligned superclusters. This distinction is subtle, but important. If the wall is a coincidence of line-of-sight projections, then its coherence is less significant. But if the components are dynamically connected, meaning they move together or share gravitational flows, then the structure is real in a physical sense, not just a visual one. Most current evidence supports the latter view. The components of the wall are moving as part of a larger coordinated flow, suggesting that they are not just neighbors, but relatives. The Sloan Great Wall is also connected, both visually and gravitationally, to surrounding features. To its west lies a network of filaments extending toward the Corona Borealis supercluster, while to its east are voids that help define its shape by contrast. This kind of alignment, walls beside voids, nodes connected by threads, is characteristic of the cosmic web, but rarely is it this stark, this long, or this statistically surprising. Some researchers have used the Sloan Great Wall to study the biasing of galaxy formation, the idea that galaxies are more likely to form in dense regions, and that their clustering amplifies the apparent mass structure. Others have used it to examine Baryon Acoustic Oscillations, ripples from the early universe imprinted in the distribution of matter. The wall, by virtue of its size, allows for long baseline measurements that help refine models of cosmic expansion and dark energy. From a visual perspective, the Sloan Great Wall is not something that can be seen with the eye, even through a telescope. It is too large, too faint, and too diffuse. It exists only in data, in scatterplots, velocity maps, and simulation overlays. And yet, once seen, it cannot be unseen. It becomes a ghost in the architecture of the universe, stretching quietly across time and space, asserting its presence not through brightness, but through endurance. For those who study the large-scale structure of the universe, the Sloan Great Wall is a landmark, not just a measurement, but a boundary. It represents the edge of what is commonly accepted, and the beginning of what must be explained. Its scale pushes the limits of our cosmological models, its discovery reshaped our maps of the cosmos, and its continued study reveals more about how the universe constructs its largest structures, not suddenly, but gradually, with time, gravity, and patience.
Chapter 17. The Huge LQG. In the far reaches of space, where light from the early universe still travels toward us across billions of years, astronomers discovered something that raised a deep and difficult question. How large can the universe's structures really be? What is the true limit to cosmic architecture before our current models begin to crack? In 2013, a team of astronomers led by Roger Clowes identified a grouping of quasars so vast, so elongated, and so seemingly coherent that it began to stretch the boundaries of what cosmologists had considered possible. This formation became known as the Huge Large Quasar Group, or Huge LQG. Its name may sound technical, even dry, but the implications of its existence ripple through the foundations of cosmology. Quasars are among the brightest objects in the universe. Powered by supermassive black holes at the centers of galaxies, they release staggering amounts of energy as matter falls inward and heats to extreme temperatures. Because they are so luminous, quasars can be seen from immense distances, some from as far as 12 billion light-years away. This makes them excellent markers for mapping the early universe, especially at high redshifts. But quasars are not randomly scattered. They tend to cluster in groups, reflecting the underlying distribution of dark matter and the gravitational scaffolding of the universe. The discovery of the Huge LQG was not simply about brightness, it was about connection. The Huge LQG contains at least 73 quasars, spread across a region over 4 billion light-years in length. More specifically, the structure stretches about 1.24 gigaparsecs, or roughly 4.04 billion light-years, making it one of the largest known coherent structures in the observable cosmos. To place this in perspective, that is more than 30 times the length of the Milky Way galaxy. It is longer than the Sloan Great Wall, longer than Laniakea, and longer than nearly any other feature mapped through observational astronomy. And yet, according to the cosmological principle, the idea that the universe should appear uniform and isotropic on the largest scales, such a structure should not exist. The cosmological principle is not just a philosophical stance, it is the backbone of many modern cosmological models. From the equations that describe cosmic expansion to the distribution of dark matter and the evolution of structure, the assumption that the universe is homogeneous and isotropic at large scales is fundamental. According to this principle, when you look at a big enough piece of the universe, say a few 100 million light-years or more, things should start to look statistically similar in every direction. Local variations are expected, but extremely large deviations are not. And yet, the Huge LQG appears to be one such deviation. The discovery of the Huge LQG began with the Sloan Digital Sky Survey, which provided redshift data for thousands of quasars. Using clustering algorithms, Clowes and his team identified a tight grouping of quasars in a relatively narrow band of redshifts, indicating they were not only near each other on the sky, but at roughly the same distance from Earth. This ruled out the possibility that they were merely a chance projection. Their spatial proximity, combined with redshift alignment, suggested a genuine three-dimensional structure. What made the Huge LQG so striking was not just its length, but its internal coherence. Many of the quasars appeared to be aligned along a similar axis, and the group exhibited signs of structural integrity, a filament or bridge rather than a random scatter. This gave rise to questions about whether the structure could have formed through known gravitational processes, or whether its existence hinted at unknown dynamics in the early universe.
Some proposed that this alignment might be the result of initial quantum fluctuations that were amplified over cosmic time. Others wondered whether the quasars were tracing an unseen superstructure, a kind of dark matter spine upon which galaxies and black holes had formed in a specific configuration. The scientific community responded with both intrigue and skepticism. Critics argued that the group might be a statistical fluke, a rare but not impossible clustering in a large dataset. Others pointed out that the definition of what constitutes a structure can be somewhat arbitrary. After all, the boundaries of the huge LQG are not physically marked. They are determined by the density of quasars above a certain threshold. Adjust that threshold, and the size or coherence of the structure could change. But even conservative models confirmed that something unusual was present. The odds of finding such a grouping purely by chance were estimated to be less than 1 in 10,000. Further complicating the picture was the orientation of the huge LQG. Some studies noted that the quasars' polarization vectors, the angles at which their light is polarized, were aligned over large distances, possibly echoing the structure's geometry. This kind of large-scale alignment is unexpected and difficult to explain with conventional astrophysical processes. It has led to speculation that the huge LQG might be related to other cosmic anomalies, such as the CMB cold spot, axis of evil, or the large-scale quasar polarization alignment previously discovered in the same region of the sky. For cosmologists, the huge LQG raises uncomfortable questions. If such a large structure truly exists, does it violate the cosmological principle? And if so, what does that mean for our models of inflation, dark matter, and the evolution of the universe? Some theorists have proposed that the huge LQG might be evidence of a primordial anisotropy, a deviation from uniformity seeded in the earliest moments of cosmic inflation. Others suggest that large-scale structures may emerge naturally in a multiverse framework, where local variations in density, physics, or geometry give rise to regions with differing structural properties. Still others emphasize the need for caution. The universe is vast, and even rare events are bound to occur somewhere. The existence of a massive structure does not necessarily break the rules. It may simply sit at the far end of the probability curve. But if more structures like the huge LQG are found, or if further analysis confirms similar alignments in other datasets, then the case for new physics becomes stronger. Already, some surveys have begun to report quasar groupings of comparable size, though none have been studied in as much detail as this one. From an observational perspective, the huge LQG is a landmark. It demonstrates how high redshift objects like quasars can be used to map the distant universe, not just in 2 dimensions, but in full 3-dimensional relief. It also shows how deep, wide-field surveys like the SDSS are reshaping our understanding of structure. No longer are we limited to local clusters and nearby galaxies. We can now trace the fabric of the cosmos across billions of years, uncovering patterns that were once hidden in noise. As technology improves, future surveys like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, and the Euclid Space Telescope will gather even more precise data, allowing astronomers to test the coherence and frequency of large quasar groupings. These missions may confirm whether the huge LQG is a singular outlier or one example of a broader population of ultra-large structures. They may also help determine whether these alignments are physically meaningful or artifacts of selection bias and survey geometry. Regardless of its ultimate classification, the huge LQG serves as a humbling reminder. The universe is more than a smooth, expanding cloud of galaxies. It is textured, it is uneven, it is shaped by both gravity and time, by randomness and law. Structures like the huge LQG pull at the edge of our models, asking us to consider the possibility that we do not yet fully understand the architecture of the cosmos. It is also, in a quiet way, beautiful. Not in the way a galaxy is beautiful, with arms of stars and clouds of gas, but in its scale, in its mystery, in the fact that across 4 billion light-years, quasars have formed and aligned in a way that our instruments can detect, our minds can trace, and our theories must try to explain. In the darkness between those quasars lies the story of the universe's evolution, a story still being told. As we move on from the huge LQG, we turn now to a region even farther away, a place so densely packed with quasars, it was once thought impossible.
Chapter 18. The Close Campesano Large Quasar Group. LQG. Long before the huge LQG surprised the scientific world with its immense scale, another enormous structure had already raised questions about the limits of cosmic order. Discovered in the early 1990s, the Close Campesano Large Quasar Group, or Close Campesano LQG, marked one of the earliest pieces of observational evidence that quasars, those brilliant lighthouses from the early universe, could organize themselves across billions of light-years. At the time, it was among the largest structures ever detected, and its discovery helped pave the way for the rethinking of large-scale uniformity in the cosmos.
The Close Campesano LQG was named after its discoverers, Roger Close and Luis Campesano. Their work, published in 1991, analyzed a redshift survey of quasars at a distance of roughly 8 to 9 billion light-years from Earth. What they found was startling. Instead of a random scatter of quasars across space, a significant number appeared to cluster within a relatively narrow redshift band and within a shared volume of space. The group comprised 34 quasars, spread over a region about 2 billion light-years in length, while it would later be dwarfed in length by the Sloan Great Wall and the huge LQG. At the time it stood as a groundbreaking example of large-scale quasar coherence. The structure was not detected by imaging alone. It emerged from redshift data, the three-dimensional mapping technique that reveals not only the position of objects in the sky, but their distance from Earth. By combining these two pieces of information, Close and Campesano could distinguish between apparent proximity and true spatial clustering, and what they found was more than coincidental alignment, it was a physical formation. The quasars occupied similar redshifts and spatial coordinates, indicating that they were likely bound within a larger framework shaped by gravity and early universe conditions. At the time, this discovery posed an immediate and somewhat unsettling question. According to the cosmological principle which underlies most models of cosmology, the universe should be homogeneous and isotropic when viewed on large enough scales. In practical terms, this means that structures larger than about 300 to 500 million light-years should become increasingly rare and eventually non-existent. The Close Campesano LQG, at roughly 2 billion light-years, seemed to defy that boundary. Initial skepticism followed. Was this structure truly real, or could it be the result of selection bias, observational gaps, or even an artifact of small number statistics? But as the dataset grew, more surveys confirmed the spatial correlation among the quasars. Moreover, the statistical significance of the structure remained strong. This was not a chance occurrence, it was a genuine quasar grouping, and it demanded a place in the cosmic map. The discovery of the Close Campesano LQG had a cascading influence on the field of cosmology. It encouraged further exploration of quasar distributions and inspired the development of more comprehensive redshift surveys. It also raised the bar for what scientists thought was possible in terms of structure size. If quasars, incredibly distant and rare objects, could cluster like this, then what other megastructures might be waiting to be discovered? Later studies showed that the Close Campesano LQG might not be an isolated anomaly. In fact, its discovery helped sharpen the tools scientists would use to uncover future superstructures, including the huge LQG. Its location and orientation were used as reference points, guiding deeper explorations in that region of the sky. In many ways, it was a cornerstone, not just for mapping the high redshift universe, but for testing the assumptions embedded in our models of structure formation. In terms of internal structure, the Close Campesano LQG is composed primarily of quasars associated with massive galaxies, likely located at the centers of large dark matter halos. These quasars are believed to be active during a particular stage of galactic evolution, a time when supermassive black holes are rapidly accreting matter and radiating energy across the electromagnetic spectrum. Because these phases are relatively short-lived on cosmic timescales, finding multiple quasars in proximity implies a shared history or environment, a synchronized ignition across the structure. This synchronicity hints at a deeper coherence. Why would black holes across billions of light-years flare up in such a correlated way? Some astronomers suggest that environmental conditions, such as the density of surrounding matter or the history of galaxy mergers, may trigger active galactic nuclei within clustered structures. Others propose that gravitational interactions and shock waves propagating through the intergalactic medium could catalyze quasar activity across large distances. One hypothesis is that the Close Campesano LQG traces a filament or sheet of dark matter, a hidden backbone in the cosmic web upon which luminous matter is arranged. In this scenario, the quasars represent just the visible tip of an enormous gravitational iceberg. Beneath them lie galaxy clusters, cold gas, and dark matter filaments, all shaped by the evolution of initial density fluctuations in the early universe. If this is true, then the structure we observe is part of a much broader framework, connecting it to other filaments, walls, and voids across the sky. The idea that such a vast quasar group could form naturally within the standard LEF-CDM model remains debated. Some simulations suggest that structures of this size can emerge, but only rarely. Perhaps one in several thousand universes would produce something similar. Others argue that the presence of the clouds Campusano LQG, together with later discoveries like the huge LQG, implies that either we live in an unusually structured region of the universe or that our theories need to be revised. Efforts to analyze the geometry of the structure have yielded further insight. The clouds Campusano LQG is not a perfect sphere, nor is it a straight line. Instead, it appears to be an elongated, somewhat curved formation, possibly part of a larger arc or sheet. Its internal density varies, with pockets of denser quasar activity and regions of lower concentration. This irregularity may offer clues about the history of the structure's formation, suggesting, for example, that it formed from the merging of smaller protostructures or evolved through anisotropic gravitational collapse. Despite the enormity of the structure, the individual quasars within it are separated by millions of light-years. The scale is so vast that no signal could have traveled from one quasar to another during their active phases. This means that any synchronicity in their behavior must be the result of earlier shared conditions, not direct interaction. It also reinforces the mystery of coherence on such scales. How did so many galaxies ignite in unison across such a distance? Modern telescopes continue to revisit the clouds Campusano LQG, using improved spectral resolution and deeper imaging to refine our understanding of its boundaries. Some studies have proposed that the structure might be even larger than originally thought, potentially extending into adjacent regions of the sky. Others have suggested that the group might be connected to still undiscovered formations, distant filaments or voids that have yet to be fully mapped. As we examine structures like this one, we are reminded of the humility required in cosmic cartography. Our maps are always incomplete, always evolving. The sky contains more than we expect, and often more than our models predict. Every large structure discovered becomes a test, not only of our instruments, but of our assumptions. The clouds Campusano LQG stands today as more than just a precursor to larger discoveries. It is a landmark in its own right, a reminder of how early clues can reshape entire paradigms. It represents the transition point between conventional clustering and the possibility of true large-scale order, and its persistence in the data challenges us to ask deeper questions about the universe's architecture. Some have wondered whether the existence of such a structure implies preferred directions in the cosmos, alignments or patterns that defy randomness. Others see it as a hint that early inflation may have seeded more complex topologies than we now assume. Still others propose that we need better models of bias in quasar formation, frameworks that explain how local conditions could produce coordinated activity across massive distances. Regardless of which explanation proves true, the clouds Campusano LQG will remain a vital chapter in the story of cosmology. It helped open the door to a new scale of observation. It inspired deeper surveys, bolder hypotheses, and more refined simulations. And perhaps most importantly, it showed that even the deepest truths about the universe begin with careful measurements and a willingness to question what we thought we understood. As we now continue through the grandest known structures of the universe, we move toward a region whose emptiness is as profound as the clouds Campusano group's density.
Chapter 19. The Eridanus Supervoid. When you gaze into the cosmos, most of what you see are lights, galaxies, stars, quasars, clusters. But some of the most mysterious features in the universe are not defined by what is present, but by what is missing. Emptiness itself can be a clue. Silence, in a place where there should be noise, can become a signal, and nowhere is that more true than in the case of the Eridanus Supervoid, a vast, puzzling region in space where the universe seems quieter, colder, and emptier than it should be. The Eridanus Supervoid is located in the direction of the constellation Eridanus, a southern sky feature named after the ancient Greek river. What makes this region extraordinary is not its content, but the absence thereof. The void spans an estimated 1.8 billion light-years in diameter, making it one of the largest known supervoids in the observable universe. It is not completely empty, no place in the cosmos is, but it has a significantly lower density of galaxies, matter, and light than surrounding regions. What first brought this region to the attention of cosmologists was not a galaxy survey, but rather a subtle, unexpected anomaly in the cosmic microwave background, or CMB, the faint afterglow of the Big Bang that fills the universe with nearly uniform radiation. In the early 2000s, observations from the Wilkinson Microwave Anisotropy Probe, WAP, followed by the more sensitive Planck satellite, revealed a cold spot in the CMB in the direction of Eridanus. This cold spot, a region slightly cooler than expected, stood out not just for its temperature, but for its size and coherence. It was too large and too cold to be easily explained by statistical fluctuations alone. Some astronomers proposed that the cold spot was a primordial feature, imprinted during the early moments of inflation. Others suggested it might be due to secondary effects, specifically the integrated Sachs-Wolf ISW effect, which occurs when light from the CMB passes through a large underdense region, causing it to lose energy due to the changing gravitational potential.
In this model, the cold spot was not a relic of the Big Bang itself, but a signal of something far closer, a supervoid that had drained energy from CMB photons passing through it. The search for this hypothesized void led astronomers to analyze galaxy surveys in the direction of the cold spot, and what they found matched the theory: a vast region with significantly fewer galaxies than expected, centered roughly 3 billion light-years from Earth. This region, now known as the Eridanus supervoid, appeared to coincide with the cold spot in both location and angular scale. It became one of the strongest candidates for explaining the CMB anomaly through local cosmic structure. However, the story is not so simple. While the alignment between the supervoid and the cold spot is suggestive, the degree of temperature change observed in the CMB appears too large to be fully explained by the ISW effect alone, even with a void as big as Eridanus. Some models predict that the supervoid should only account for about 10 to 20% of the temperature depression. This has led to debate. Is the supervoid part of the explanation, or is it a coincidence? And if it is only part of the story, what else might be causing the cold spot? The implications are profound. If the Eridanus supervoid cannot account for the entire cold spot, then either there is another large-scale feature contributing to the anomaly, or the cold spot may indeed be primordial, a fingerprint of unknown physics from the earliest moments of time. Some cosmologists have speculated that the cold spot might even be evidence of a collision with another universe, a bubble universe brushing against ours during inflation. This remains speculative, but it illustrates the level of mystery this patch of sky evokes. What we do know about the Eridanus supervoid comes from multiple lines of evidence. Galaxy surveys using instruments such as the Dark Energy Survey, 2MASS, and WISE have confirmed a genuine underdensity of galaxies in the region. The void is roughly spherical in shape, although some measurements suggest it may have a complex filamented internal structure, more like a cavern with subchambers than a single smooth bubble. Its estimated redshift places it at about Z.15 to SOM.3, or roughly 1.5 to 3 billion light-years away, depending on the part of the void being measured. This region is significant not just because of its size, but because of how it interacts with light. The ISW effect, while subtle, is one of the few ways the distribution of matter in the nearby universe can directly affect the CMB. If confirmed, the Eridanus supervoid would be one of the first large-scale structures to leave a measurable imprint on this ancient radiation. It would also suggest that voids, often dismissed as uninteresting negative space, can have real gravitational consequences. Supervoids like Eridanus form naturally in simulations of cosmic structure formation. As matter clumps under gravity, regions with slightly less matter expand more rapidly and become emptier over time. These expanding voids can grow to hundreds of millions or even billions of light-years across, pushing galaxies into walls and filaments around their perimeters. In this way, voids are not gaps in the universe's structure, they help define it. They are the negative space that gives shape to everything else. Yet Eridanus stands out. Its size, its depth, and its alignment with the cold spot make it more than just a void. It becomes a kind of cosmic question mark, a boundary between what we can explain and what we can only measure. It is not just an empty space, but a silence that echoes louder than some of the universe's brightest lights. Theoretical work continues to refine models of how supervoids affect the CMB. Recent simulations have explored whether non-spherical voids or stacked voids aligned along a line of sight could enhance the ISW effect. Some studies suggest that void stacking, where multiple underdense regions lie along the same visual axis, could collectively deepen the CMB signal. Others propose that interactions with surrounding filaments or residual anisotropies in the early universe might amplify the effect further. At the same time, alternative explanations for the cold spot remain under discussion. One idea is that the anomaly is the result of cosmic variance, a statistical fluke that appears unusual but is still within the realm of possibility. In this view, the cold spot is not caused by a structure at all, but is simply one of the rare extreme deviations that occur in a random field. This explanation is elegant in its simplicity, but unsatisfying in its lack of mechanism. Another more speculative theory suggests that the cold spot could be the signature of a topological defect, such as a cosmic texture, a remnant of symmetry breaking in the early universe. Textures are hypothetical, but they would leave distinct imprints on the CMB through gravitational effects. If the Eridanus supervoid and the cold spot are not causally related, then perhaps both are separate features of a more complex cosmological picture. What is clear is that voids like Eridanus challenge our perception of the universe as a uniformly structured place. They remind us that emptiness can be powerful, that gravity is not always attractive, and that structure can arise from absence as much as from presence. They also serve as laboratories for testing dark energy, modified gravity theories, and the limits of cosmic isotropy. From a visual standpoint, the Eridanus supervoid is invisible. It cannot be seen with the naked eye or a telescope. It reveals itself only through absence, through the thinning out of galaxies in large sky surveys, and through the subtle cooling of radiation in the CMB. It is a presence made of nothing, a measurable hole in the web of cosmic matter. As cosmologists continue to refine their tools, structures like the Eridanus supervoid may become more than mysteries. They may become tools themselves. By studying how light, gravity, and temperature behave in these regions, scientists hope to gain new insight into the nature of space, the evolution of matter, and the behavior of the universe on its grandest scales. And perhaps more poetically, the supervoid reminds us of something older than physics, the idea that emptiness is not the absence of meaning, but the space where meaning can emerge. That silence is not the lack of music, but the pause between notes. And in the Eridanus supervoid, we find a cosmic pause, a stillness that invites not answers, but questions. We now continue to the next feature in our journey, not a void, but a wave, an ancient ripple of matter that stretches across a vast arc of space, and yet was hidden in plain sight for decades.
Chapter 20. The Radcliffe Wave. For decades, the structure of our own galaxy was charted from within, like trying to understand a forest by standing beneath the trees. We saw stars, clouds of gas, and the arch of the Milky Way in the night sky. But what we could not see, what eluded us until recently, was a pattern so massive and so elegantly simple that its discovery changed the way we understand our galactic neighborhood. This pattern is called the Radcliffe Wave, a gently undulating ribbon of stellar nurseries and interstellar gas, stretching across thousands of light-years, coiling through the Milky Way like a ripple frozen in time. It was not discovered by peering into deep space, but by looking closer, with sharper eyes and new tools. In 2020, researchers at Harvard's Radcliffe Institute, led by João Alves and Catherine Zucker, revealed that many of the star-forming regions previously believed to be scattered randomly around the Sun were in fact part of one coherent wave. By analyzing stellar distances with unprecedented accuracy from the Gaia Space Observatory, the Radcliffe Wave is not just a linear arrangement of gas and stars. It is a sine wave, an undulating structure that rises and falls above and below the galactic midplane, stretching over 9,000 light-years from end to end. Its amplitude, the vertical height from the galactic plane, is about 500 light-years, and it includes some of the most famous and active stellar nurseries in the sky, the Orion Nebula, the Perseus Molecular Cloud, Cepheus, Taurus, and Ophiuchus, among others. For the first time, it became clear that these well-known regions were not separate islands in space, but crests and troughs along the same wave. This realization required a shift in thinking. For decades, astronomers mapped nearby molecular clouds using angular positions and estimated distances, often based on indirect measurements. Without accurate three-dimensional data, it was difficult to see the forest for the trees, but Gaia changed that. By providing precise parallaxes for over 1 billion stars, the mission allowed researchers to determine distances with milliparsec accuracy. That breakthrough allowed the cloud positions to be plotted in full 3D space, revealing the elegant, sinuous form of the Radcliffe Wave. What could cause such a structure? Theories are still forming, but several ideas have emerged. One possibility is that the wave was induced by a passing dwarf galaxy or dark matter clump that perturbed the Milky Way's disk, sending oscillations through the interstellar medium. Much like a pebble dropped into a pond sends ripples outward, a gravitational interaction could have caused gas and dust to bunch up into a wave pattern that remains visible millions of years later. Another idea suggests that spiral arm dynamics, coupled with magnetic fields and galactic rotation, could naturally give rise to wave-like features in the gas distribution. There is also the intriguing observation that the Radcliffe Wave is not symmetric. It has twists and irregularities, and some of the star-forming regions appear denser or more active than others. This suggests that while the wave is coherent, it is not static. It may be evolving, fragmenting, or interacting with other structures in the galactic disk. Over time, new stars are born from its gas, heating the surrounding material and sending out winds and radiation that reshape the local environment. In this way, the Radcliffe Wave is both a product and a driver of galactic evolution. What makes this discovery especially significant is that it recenters our perspective. The Sun lies remarkably close to the wave, just about 500 light-years away, depending on how the wave's position is measured. In fact, the solar system is nestled right next to the wave's trough, in a local cavity of low-density gas called the local bubble. This bubble is believed to have formed from supernova explosions over the past 10 to 20 million years, clearing out the gas and creating a region of relative emptiness around the Sun. The proximity between the local bubble and the Radcliffe Wave suggests a possible interaction. Perhaps the bubble's expansion has pushed or shaped part of the wave. Another compelling implication is that the Radcliffe Wave may be only one segment of a much larger structure.
Some researchers speculate that it could be part of a galactic-scale wave, a standing oscillation running through the Milky Way's spiral arms, triggered by past collisions or long-term instabilities in the galactic disk. If this is true, then the Radcliffe wave might be a local crest of a much vaster system of undulations that we have only begun to detect. The Gaia mission continues to expand our ability to test this hypothesis as it charts more stars at greater distances with every data release. The existence of such a coherent wave so close to Earth also opens up new avenues for understanding stellar birth and death. Since many of the molecular clouds along the wave are active star-forming regions, the wave provides a natural laboratory for studying how stars form in different environments, in high-density versus low-density regions, near the crests versus near the troughs, or in areas impacted by radiation from neighboring stars. It also allows for the exploration of how feedback from young stars in the form of winds, jets, and radiation influences the structure of the wave itself. On a human scale, the discovery evokes awe. For centuries, we've looked up at constellations like Orion, not knowing that the glowing nebula at his belt was part of a vast ribbon curling through the galaxy like a wave in slow motion. This wave, invisible to the eye yet mapped by math and light, links together some of the brightest and most beloved features of the night sky. It reshapes the way we imagine our place in the Milky Way, not as isolated stargazers beneath scattered lights, but as neighbors to a grand dynamic motion unfolding across millions of years. In some ways, the Radcliffe wave feels like a bridge between local and cosmic structures. It is larger than anything visible in a single night sky, yet still part of our immediate galactic environment. It's not as vast as a supercluster or a cosmic wall, but it is more intimately connected to our daily sky. Every time a child gazes at the Orion Nebula through a telescope, they are peering into the crest of this galactic wave. Every time a radio telescope tunes into emissions from the Taurus molecular cloud, it hears the signal of another segment. These clouds are not just neighbors in the sky, they are fellow travelers on the same undulating path. The story of the Radcliffe wave is still unfolding. New observations are revealing more clouds that may belong to the wave or run parallel to it. Simulations are testing how such a structure could form, how long it might persist, and what forces shape its curvature. Some theories suggest that the wave's undulations could oscillate with time, possibly reversing or flattening depending on galactic conditions. Others propose that the wave could trigger future generations of star formation, acting like a galactic nursery conveyor belt, sweeping through the disk and leaving stars in its wake. The wave's discovery also encourages a reanalysis of other parts of the galaxy. If such a feature was hidden in plain sight near the Sun, how many more might exist farther out, obscured by dust, distance, or outdated assumptions? Already, structures like the local arm, Scutum Centaurus arm, and Perseus arm are being re-evaluated in light of the Radcliffe discovery. Perhaps these arms, too, contain wave-like undulations. Perhaps the galaxy is not a flat pinwheel, but a rippling, breathing organism, with waves and folds shaping the birthplaces of stars. From a broader perspective, the Radcliffe wave also touches on a deeper truth about scientific discovery. It reminds us that the most transformative insights are not always about distant galaxies or abstract equations. Sometimes they are right next to us, hidden in familiar places, waiting for sharper vision. Sometimes the universe holds its secrets not in darkness, but in plain light, visible from Earth for millennia, yet only now understood. It also reminds us of how much remains unseen. The Radcliffe wave may be vast, but it is only one feature in one arm of one galaxy. Beyond it lie layers of structure, rivers of stars, arcs of dust and gas, and perhaps more waves, still unmapped. With Gaia and its successors, the fabric of the Milky Way will continue to be stitched together in higher resolution, each new thread revealing another motion, another memory, another wave. We end this chapter not with the conclusion of a journey, but with the continuation of motion. For just as the wave carries gas and stars, it now carries our understanding, pulling us from the familiar into the mysterious. And as we follow it, we find that even the quietest ripples can change the shape of what we know.
Chapter 21. The Sagittarius Stream. Far beyond the shimmering disk of the Milky Way, past the stars that form our spiral arms and the gas clouds that give birth to new suns, there exists a faint and winding ribbon of stars that stretches like a ghostly arc across the sky. This ribbon is not part of the galactic spiral, nor is it a recently formed structure. Instead, it is the torn remains of a small galaxy that once dared to dance too close to our own. It is called the Sagittarius Stream, and it offers one of the clearest and most beautiful examples of how galaxies consume each other, not with explosions or violence, but with slow, elegant disassembly across cosmic time. The story of the Sagittarius Stream begins with its source, the Sagittarius dwarf spheroidal galaxy, a small and relatively faint satellite of the Milky Way, discovered in 1994 by astronomer Rodrigo Ibata and his colleagues.
At the time, it was among the closest known satellite galaxies to our own, located just 70,000 light-years from Earth and orbiting our galaxy in a polar trajectory. But it was also peculiar. The galaxy was elongated, stretched and irregular, a sign that it was not merely orbiting, but being slowly dismantled by the immense gravitational field of the Milky Way. This process is known as tidal disruption, and it occurs when a smaller object, such as a dwarf galaxy, passes close enough to a much larger one that gravitational forces begin to pull it apart. The outer stars of the smaller galaxy feel a stronger tug toward the host than toward their own center, and over time these stars are peeled away, forming elongated streams that trace the path of their former orbit. These stellar streams, like breadcrumbs across the sky, map out the route of destruction, and the Sagittarius stream is one of the most dramatic and complete examples known. Stretching over 360 degrees around the Milky Way, the Sagittarius stream wraps itself around our galaxy like a cosmic ribbon. It contains stars that once belonged to the Sagittarius dwarf galaxy, now torn free and cast into orbit, forming both a leading arm and a trailing arm that curve above and below the galactic plane. Some segments of the stream pass within 30,000 light-years of Earth, making them accessible to deep imaging and spectroscopic analysis. Other parts extend far into the galactic halo, up to 100,000 light-years away, tracing the outer boundaries of our galaxy's gravitational influence. Observing the Sagittarius stream requires more than a telescope. Because the stream is faint, its stars are often lost in the background clutter of the Milky Way. To reveal its structure, astronomers rely on stellar population filtering techniques that isolate stars of a particular type, age, or metallicity. Red giant stars, for instance, are often used as tracers, as they shine brightly and can be identified by their spectral fingerprints. By combining data from surveys like the Sloan Digital Sky Survey, SDSS, and Gaia, researchers have been able to build detailed 3D maps of the stream, showing not only where it lies, but how its stars are moving. These motions reveal something striking. The stars in the Sagittarius stream do not merely orbit the galaxy, they oscillate. They follow wave-like patterns, rising and falling above and below the galactic plane. These oscillations provide clues to the past interactions between the Sagittarius dwarf galaxy and the Milky Way. Every time the dwarf galaxy passes through the galactic disk, it triggers waves, disturbances that ripple through the stars of the Milky Way like a bell being struck. These events can cause star formation, shift stellar orbits, and leave behind features like corrugations, ridges, and warps in the galactic disk. The Sagittarius stream is not just a story of destruction, but of influence. Despite its small size, the Sagittarius dwarf galaxy has likely played a significant role in shaping the Milky Way's present structure. Some researchers suggest that repeated passes of the dwarf galaxy may have contributed to the formation of the Milky Way's central bar, or influenced the position of spiral arms. Others propose that the presence of the stream, particularly its timing and velocity, can help us probe the distribution of dark matter in the galactic halo. Because stellar streams are sensitive to the underlying gravitational field, they serve as natural detectors of dark matter substructures. If a clump of dark matter passes through a stream, it can create a gap, a localized disruption in the stream's continuity. By identifying and measuring these gaps, astronomers hope to map the distribution of dark matter in the halo and test predictions of the lambda-cold dark matter lens CDM model. In this way, the Sagittarius stream becomes a gravitational seismograph, recording not just its own dissolution, but the invisible landscape through which it travels. Tracing the origin of the stream also helps reconstruct the history of the Sagittarius dwarf galaxy itself. Studies suggest that it may have originally contained billions of stars, and a mass perhaps 1,000th that of the Milky Way. Over the course of several orbital passes, each lasting hundreds of millions of years, it has lost much of its mass to tidal stripping, and its core has been reduced to a dense remnant, still visible but diminished, drifting toward eventual absorption into the galactic disk. And yet, despite its apparent fragility, the Sagittarius dwarf galaxy is still here. It continues to orbit, continues to lose stars, and continues to reshape the structure of the Milky Way in its quiet way. The stream it leaves behind is both a record of the past and a predictor of future encounters, a living fossil of galactic interaction. In some ways, the Sagittarius stream is like a mural in the sky, a long, continuous line of stars that traces a story billions of years in the making. It connects the inner regions of our galaxy with its outer halo. It ties the history of the Milky Way to the fates of smaller galaxies around it, and it shows in delicate detail how gravitational tides, slow, persistent, and unyielding, can sculpt entire systems. It is not the only stream in the galactic halo. Other dwarf galaxies have left their own trails, the Orphan stream, the Helmi stream, and the GD1 stream, among others. Each of these adds a stroke to the portrait of the Milky Way's growth, a process not of smooth accumulation, but of merging, shredding, and absorption. The halo becomes not an empty shell, but a tapestry woven from the remnants of once independent galaxies. The Sagittarius stream also invites philosophical reflection. It reminds us that the universe builds by breaking, that stars, like memories, can be torn from their origins and yet continue to shine in new orbits, that gravity, though slow and silent, is the great artist of the cosmos, sculpting not with force but with time. And perhaps most profoundly, the stream speaks to the continuity of motion. The stars that make up this structure were once part of a single, coherent system. They were born together, traveled together, and are now scattered, yet they remain linked by their shared origin. We too are part of such motions, tied to our galaxy's path, to its past, and to its future. As we look ahead, we find yet another colossal structure in the universe's distant reaches. Not a stream, not a galaxy, but a colossus of light and matter that challenges our very assumptions about size and scale.
Chapter 22. The Hercules, Corona Borealis Great Wall. In the vast theatre of the universe, where light travels across billions of years to reach our eyes, there are structures so immense that their very existence raises questions about the foundations of cosmology. These are not stars or galaxies or even clusters, but walls, not physical in the sense of stone or steel, but formed from hundreds of thousands of galaxies drawn together by gravity across mind-stretching expanses. Among the largest of these is the Hercules Corona Borealis Great Wall, a name that may sound like mythology, but represents a real and bewildering feature of our universe, one that seems almost too large to exist within the rules we thought we understood. This structure, discovered in 2013, is one of the biggest known features in the observable universe. Its name comes from the constellations Hercules and Corona Borealis, between which much of the wall's mass is found when seen from Earth. Yet despite its mythological name, the Hercules Corona Borealis Great Wall is not fiction. It is a complex arrangement of galaxy clusters, superclusters, and vast filaments that span an estimated 10 billion light-years in length, possibly more depending on how one defines its edges. It is so enormous that light itself would take nearly 3/4 of the universe's age just to cross it. The discovery was made through the study of gamma-ray bursts, brief yet intensely energetic explosions, thought to mark the deaths of massive stars in distant galaxies. These gamma-ray bursts are among the brightest events in the universe, visible across extreme distances, and therefore useful as traces of where matter is distributed on the largest scales. When researchers examined the distribution of over 280 gamma-ray bursts, they noticed an unexpected clustering in the direction of Hercules and Corona Borealis, a region where more bursts occurred than randomness would suggest. Further statistical analysis suggested that these gamma-ray bursts were not just coincidentally near each other, but were located at roughly the same redshift, a measure of how much the universe has expanded since the light from these events was emitted. This clustering implied that their host galaxies were physically near one another, not just aligned from Earth's point of view. It was this alignment, both in space and in cosmic time, that led to the hypothesis of an enormous structure, a wall of galaxies so vast that it stretches the bounds of known cosmological theory. But what exactly is a great wall in cosmological terms? The term does not refer to a single solid entity. Rather, it describes a superstructure, a region where clusters of galaxies, themselves composed of hundreds or thousands of galaxies, are connected by filaments of gas, dust, and dark matter. These filaments create a web-like arrangement, often called the cosmic web, the largest scale structure in the universe. In some regions, these filaments come together to form sheets or walls, extended quasi-two-dimensional formations that can span hundreds of millions or even billions of light-years. The Hercules Corona Borealis Great Wall is one of several known cosmic walls, but its size makes it special. For comparison, the Sloan Great Wall, discovered in 2003, is around 1.4 billion light-years in length. The CFA2 Great Wall, observed in the 1980s, spans about 500 million light-years. The Hercules Corona Borealis Great Wall, by contrast, is estimated at up to 10 billion light-years, depending on how its boundaries are interpreted. It is not simply larger, it is in a different league of scale altogether. This size presents a problem, or perhaps an invitation for cosmologists. According to the cosmological principle, a core tenet of modern physics, the universe is expected to be homogeneous and isotropic on sufficiently large scales. In simpler terms, this means that when we zoom out far enough, the universe should look roughly the same in all directions, with matter evenly distributed on average. Current models suggest that this smoothness should dominate on scales larger than 1.2 billion light-years. Structures like the Sloan Wall and the giant GRB ring, while large, can still fit within that model, but the Hercules Corona Borealis Great Wall seems to go far beyond what is predicted.
This has led to intense debate. Some scientists argue that the wall might not be a single coherent structure, but rather an illusion created by observational biases or statistical anomalies in the gamma-ray burst data. After all, detecting a real structure at such vast distances and across such a long span of time is difficult. The redshift range over which the gamma-ray bursts occur is quite broad, which raises the question, are these galaxies truly part of the same structure, or simply projected along the same line of sight? Others, however, believe the wall is real and its implications profound. If the Hercules Corona Borealis Great Wall is indeed a single structure, it may force a rethinking of the limits of cosmic structure formation. Could gravity alone, operating over billions of years, gather matter into such an enormous arrangement? Or does the wall suggest something more exotic, perhaps even beyond the standard model of cosmology? One possibility is that we need to refine our understanding of dark matter and dark energy, which together govern the behavior of cosmic expansion and the formation of large-scale structures. If dark matter clumps more efficiently than previously thought, or if dark energy behaves differently on vast scales, it might allow larger structures to form without violating the principles of cosmology. Alternatively, the wall may suggest the presence of initial anisotropies in the early universe, seeds of unevenness that grew into giant formations under gravity's slow pull. Another possibility, more speculative but still under consideration, is that such massive structures could be remnants of topological defects or inflationary variations in the early universe. In this scenario, subtle fluctuations in the density of space-time itself, frozen in during the period of rapid inflation after the Big Bang, might have given rise to massive connected regions of higher-than-average matter density. These early variations could then evolve into the kinds of great walls we observe today. The challenge lies in confirmation. Because the Hercules Corona Borealis Great Wall is inferred from gamma-ray bursts, transient brief events, verifying the wall through other observations is difficult. Unlike galaxies or clusters, gamma-ray bursts do not persist. They flash and fade. Their afterglows can be used to locate their host galaxies, but the data is sparse. As of now, there is no galaxy catalog that directly maps out the full extent of the wall. Instead, it remains a statistical anomaly with significant implications. If future surveys, such as those from the Vera C. Rubin Observatory or the Euclid mission, can trace the same clustering in galaxy positions or redshift space, it would bolster the case for the wall's existence. Until then, the structure remains both a landmark and a mystery, a shadow across the sky whose full shape has not yet been traced. Whether the Hercules Corona Borealis Great Wall proves to be a coherent structure or a statistical illusion, its presence in our cosmological discussions is important. It reminds us that the universe is not fully mapped, that its architecture still holds surprises. It forces us to confront the limits of our models, to question what we mean by uniformity, and to test the assumptions that form the bedrock of cosmology, and it serves as a kind of cosmic horizon, not in the physical sense, but in the intellectual one. It represents the edge of our current understanding, a silhouette beyond which lie new questions. How big can structures get? How far can gravity reach? How stable are the cosmic walls that line the web of galaxies? And most importantly, what do these great structures tell us about the initial conditions of the universe itself? From Earth, the Hercules Corona Borealis Great Wall cannot be seen with the naked eye. It does not light the sky like a constellation or blaze in photographs like a galaxy. It is a statistical shape, a thread of patterns pulled from faint data, stitched together by inference and bold theory. And yet it may be one of the most significant shapes in the cosmos, not because of how it shines, but because of how it challenges what we believe. In many ways, cosmic structures like this wall resemble fossils embedded in the universe. They are remnants of long processes, imprints of formation etched across billions of years. They do not move quickly or change perceptibly within a human lifetime, but they whisper truths about the early universe, the balance of matter and energy, and the invisible threads that bind galaxies across impossible distances. And if the Hercules Corona Borealis Great Wall is real, then it may point to a truth that is even more profound, that the universe is capable of building things beyond the scale of our expectations, that its reach exceeds our models, and that the cosmos, like all great artists, is sometimes too bold to be confined by theory. As we move forward, we look not only at size but at complexity. In the next chapter, we turn to a different kind of structure, not a wall, but a wave, not a galaxy, but a ripple of light that maps the geometry of the cosmos itself. We continue our journey with the Baryon Acoustic Oscillations, subtle fluctuations, frozen in the ancient light of the Big Bang, still visible today, guiding our understanding of distance, expansion, and the shape of space-time.
Chapter 23. Baryon Acoustic Oscillations. Long before stars existed, long before galaxies began to form, the universe was filled with a hot, dense plasma, a chaotic sea of light and particles, where matter and radiation were locked together in constant interaction. Photons collided endlessly with electrons and protons,
unable to travel far before being scattered again. It was in this early epoch, less than 400,000 years after the Big Bang, that something subtle and beautiful took shape, a sound wave, not heard through ears, but through matter itself. These were the Baryon Acoustic Oscillations, pressure waves that rippled through the early universe, leaving behind a signature so faint and yet so precise that it still marks the cosmos billions of years later. To understand these oscillations, we must first imagine what the early universe looked like. It was a uniform, searing fog of hydrogen and helium nuclei, electrons, and high-energy photons. Gravity worked to pull matter together, forming denser regions, while radiation pressure pushed outward. The result was a delicate balance. Overdense regions of matter began to collapse under gravity, but the photons trapped in the plasma pushed back, creating waves that expanded outward at close to the speed of light. These waves, composed of both matter and radiation, traveled through the plasma like ripples in a vast ocean. These sound waves, or acoustic oscillations, are not metaphors. They were real compressions and rarefactions in the primordial matter radiation fluid, spreading from initial fluctuations in density. Wherever there was a slightly denser region, a spherical wave began to propagate outward. This expansion continued for hundreds of thousands of years, until the universe cooled enough for electrons to combine with protons and form neutral atoms, a moment known as recombination. At that point, the photons decoupled from matter and began to travel freely through space, becoming what we now observe as the cosmic microwave background. But the sound waves themselves, once frozen in place, left behind a distinct imprint, a shell of slightly higher matter density, at a fixed radius from the original fluctuation. This frozen shell became the key to Baryon Acoustic Oscillations. That slight overdensity, like a ripple etched into the universe's structure, influenced where galaxies would later form. On average, galaxies are more likely to be found about 500 million light-years apart, the modern equivalent of the radius of those ancient sound waves stretched by cosmic expansion. This preferred separation, though subtle, shows up as a faint peak in the correlation function of galaxy distributions. It means that if you pick a galaxy at random, there is a slightly higher probability of finding another galaxy at that characteristic distance away. It is not a pattern visible to the naked eye, but it is unmistakable in the statistics. These Baryon Acoustic Oscillations act like a standard ruler, a fixed scale feature that cosmologists can use to measure the expansion of the universe. Because we know the original physical scale of the oscillations, we can compare that to how large they appear from Earth to determine how much the universe has expanded over time. This is crucial in mapping the Hubble parameter at different redshifts, helping to build a timeline of cosmic history and the rate at which the universe has grown. The discovery and use of Baryon Acoustic Oscillations as a cosmological tool began in earnest in the early 2000s. Projects like the Sloan Digital Sky Survey, SDSS, and the Baryon Oscillation Spectroscopic Survey, Boötes Void, mapped the positions of millions of galaxies, allowing scientists to compute large-scale structure statistics with unprecedented accuracy. By examining how galaxy clustering changed over distance and redshift, researchers confirmed the presence of the Boötes peak, a small but consistent bump in the correlation function at a fixed scale. This detection provided a powerful, independent confirmation of dark energy's role in driving the acceleration of the universe's expansion. One of the most remarkable aspects of Baryon Acoustic Oscillations is how clean and consistent the signal is. Despite the complexity of galaxy formation, the chaotic motions of matter, and the gravitational evolution of structure over billions of years, the Boötes signal persists, a fingerprint from the infant universe that remains readable even in the modern distribution of galaxies. It is not easily erased or distorted, making it one of the most robust cosmological probes available. Today, Boötes measurements are one of the key pillars of the Lambda Cold Dark Matter LENS-CDM model, alongside the cosmic microwave background and supernova observations. Together, they help constrain key cosmological parameters: the Hubble constant, the matter density of the universe, the curvature of space, and the nature of dark energy. By comparing the Boötes scale at different redshifts, cosmologists can map the expansion history of the universe, determining when acceleration began and how rapidly it has progressed. Beyond galaxies, the Boötes signal has also been detected in the distribution of the Lyman alpha forest, the absorption lines seen in the spectra of distant quasars caused by intervening hydrogen gas. This method probes the universe at even earlier times, extending the reach of Boötes studies to redshifts around 2.5. The fact that the same acoustic signature appears in both galaxies and intergalactic gas shows how deeply embedded the oscillations are in the fabric of space itself. future surveys promise even more precision. The Dark Energy Spectroscopic Instrument DESI, launched in the 2020s, is collecting spectra from over 30 million galaxies and quasars, dramatically increasing the sample size and statistical power of BAO measurements. The upcoming Euclid mission by the European Space Agency and NASA's Nancy Grace Roman Space Telescope will extend the BAO mapping into deep space, allowing even finer resolution of cosmic expansion and the properties of dark energy. All of this rests on a simple, almost poetic idea that sound waves from the infant universe still echo today, not in the air, not through sound, but through the very placement of galaxies in space. These ripples in the early plasma became the framework upon which all later structure formed. Every cluster of galaxies, every wall and filament, every cosmic void owes part of its origin to the pattern seeded by these ancient oscillations. The BAO signal, therefore, is not just a tool for cosmology, it is a fossil, a preserved motion frozen into space by the cooling of the universe. It represents the moment when light was set free and matter was left to follow the map drawn by sound. It connects us to an era we can never witness, but which shaped everything we now see. Even more profoundly, Baryon Acoustic Oscillations remind us that the universe is coherent across time. The same processes that governed particles less than a second after the Big Bang still influence the structure of space billions of years later. The same fluctuations in density, driven by quantum variations in the early universe and amplified by sound, gave rise to galaxies, stars, and ultimately to us. The BAO signal is not just data, it is the lingering vibration of the universe's first breath. As we trace these waves, we gain more than just measurements, we gain perspective. We begin to see the universe not as a chaotic scatter of objects, but as a harmonic structure, one that resonates across scales and epochs. The pattern is quiet, buried beneath complexity, but it is there, a rhythm that guides cosmic evolution, a music of the spheres written in density and space. As we move forward, we will explore yet another layer of this universal architecture, a structure not formed by sound, but by absence. In the next chapter, we turn to one of the great puzzles of observational astronomy, the cold spot in the cosmic microwave background. What causes this anomalous chill in the sky? Is it just a statistical fluke, or does it point to something far deeper, a collision of universes, a void of impossible scale, or a remnant of something before time?
Chapter 24. The Cold Spot. When we look into the depths of the universe, we are not merely gazing across distance, we are peering into time, into the earliest moments after the Big Bang. The light that fills all of space, the cosmic microwave background, or CMB, is a fossil glow, a map of the infant universe frozen in its first 380,000 years. And on this map, remarkably smooth and nearly uniform, there is a blemish, a region that appears colder than its surroundings, a patch in the sky so unusual that it has drawn the attention of physicists, cosmologists, and dreamers alike. It is known simply as the cold spot. Discovered in 2004 using data from the Wilkinson Microwave Anisotropy Probe, WAP, the cold spot appeared as an area of lower temperature in the CMB, about 70 microkelvin cooler than the surrounding average. Though small in absolute temperature difference, this deviation is significant in the finely tuned precision of cosmic data. The region itself spans nearly 5 degrees across the sky, and within that vast circle lies a void in the expected smoothness of the early universe's radiation. It stands out, not because the universe is uniform, but because this patch is unusually cold compared to other variations, which are normally random and well-behaved. Initially, this anomaly was expected to be a statistical fluctuation, a rare but not impossible result in a universe governed by randomness. After all, the CMB is full of temperature fluctuations, small differences in density and heat, that seeded all future structure. However, as more precise data arrived, especially from the Planck satellite, it became clear that this cold patch was not easily explained by randomness alone. Its scale, shape, and intensity seemed to push against the boundaries of standard cosmology. Statistically, the chance of such a cold region appearing by coincidence in a lambda cold dark matter universe is less than 1%, and possibly far lower depending on the model. One proposed explanation is the integrated Sachs-Wolf effect, a phenomenon where photons from the CMB gain or lose energy as they travel through gravitational potential wells. If a photon passes through a large cosmic void, it may lose energy and appear colder when it reaches Earth. This raised the possibility that the cold spot is not a primordial feature, but the result of a massive underdense region in the universe, a supervoid. In 2015, a team using the Dark Energy Survey reported evidence of such a void, possibly stretching over 1.8 billion light-years in diameter, lying in the direction of the cold spot. This so-called Eridanus supervoid could account for part of the temperature dip.
However, this explanation, while appealing, does not fully resolve the mystery. The strength of the temperature anomaly observed in the cold spot seems too great to be explained by even a supervoid of that size. Simulations suggest that while a large void could create some cooling through the integrated Sachs-Wolf effect, it falls short of matching the depth and statistical oddity of the real cold spot. This has led some researchers to suggest that the void is only part of the story, a foreground feature layered on top of something more profound. That something more profound has opened the door to a range of bold and speculative ideas. Among the most intriguing is the possibility that the cold spot is the signature of a cosmic collision, not a collision of matter, but of entire universes. In some versions of eternal inflation theory, our universe is just one bubble in a larger multiverse. Occasionally, these bubbles might collide, leaving scars on each other's cosmic background. The cold spot in this view could be a bruise, a remnant of a neighboring universe brushing against our own in the earliest instance of existence. This idea, while speculative, is not purely science fiction. The multiverse is a natural consequence of some inflationary models, and collisions would in theory produce cold or hot spots in the CMB. These would appear as circular regions with specific statistical profiles. Studies have looked for such patterns, including around the cold spot, but so far no definitive evidence of a multiverse collision has been found. Still, the cold spot remains one of the few places in the sky where such speculation continues to persist. Another possibility is that the cold spot is not a true anomaly, but a feature of the statistical method used to analyze the CMB. The data is complex, and our interpretations often depend on assumptions about isotropy, Gaussianity, and the underlying distribution of fluctuations. It's possible, some argue, that the cold spot is not as strange as it seems when analyzed within more nuanced or non-standard statistical frameworks. This debate continues, with new models of data smoothing, wavelet analysis, and Bayesian interpretations offered to challenge or defend the cold spot's significance. The cold spot also prompts a deeper reflection on the nature of cosmic structure. Whether or not it represents a true anomaly, its study has led to detailed explorations of large-scale features, like voids, filaments, and the cosmic web. Surveys of galaxies in the cold spot's direction continue to map the density field of the local and distant universe. If the spot is truly linked to a void, then it may help calibrate our understanding of how structure formed, how voids evolve, and how matter and energy interact on the grandest scales. From a philosophical perspective, the cold spot invites humility. It is a reminder that our models, as elegant and well-tested as they are still approximations. The universe does not owe us uniformity, and its deepest truths may be stranger than we expect. That a slight dip in microwave temperature could stir debates about multiverses and early universe physics is a testament to how sensitive and rich our cosmological tools have become. A few microkelvin can ripple across theory and imagination, and in the realm of precision cosmology, every ripple matters. The cold spot has become a touchstone, a challenge to the standard model, a testing ground for new ideas. It forces scientists to revisit old assumptions, to test new physics, and to ask what anomalies really mean. Is it a flaw in the data, a window into another universe, a statistical ghost, or something else entirely? The answer remains elusive. In the meantime, observations continue. The next generation of telescopes, like the Simons Observatory and CMB-S4, will provide even higher resolution maps of the cosmic microwave background. These may reveal finer details of the cold spot, or perhaps show that it is less unique than we thought, one cold patch among many. Or they may sharpen its profile, making its peculiarity even harder to dismiss. Whatever the outcome, the cold spot serves as a guidepost in the sky, a cosmic question mark. It reminds us that the universe is not fully charted, that its oldest light still holds surprises, and that some puzzles endure not because we are looking in the wrong place, but because the answer itself lies just beyond the edge of what we can see. The cold spot is not just a region of lower temperature, it is a story, a convergence of data, theory, and imagination. It is the meeting point of observation and speculation, where precise measurements meet ancient wonder. And whether it turns out to be a void, a statistical trick, or a trace of something beyond, it will remain part of the map, a cool, quiet whisper from the dawn of time. As we near the end of our journey through the universe's largest structures, we come to a question not of shape or temperature, but of speed. In the final chapter, we turn our attention to a cosmic motion that baffles astronomers, a strange and persistent flow that seems to pull galaxy clusters in a single direction. We close this series by exploring the mystery of dark flow, and what it might tell us about what lies beyond the observable edge.
Chapter 25. Dark Flow. There is a mystery at the edge of everything we can see. It is not a visible structure, nor a detectable object, but a motion, a vast and persistent movement of galaxy clusters flowing in a common direction, as if drawn by something beyond the observable universe. This motion is not explained by any known gravitational influence within the standard model of cosmology.
It does not conform to the flow we expect from the expansion of space. It is known as dark flow, and it may be one of the most puzzling anomalies in modern astronomy. To understand why dark flow is so unsettling, we must begin with how cosmic motion is usually measured. In a uniformly expanding universe, galaxies recede from one another due to the stretching of space itself. This motion is described by Hubble's law, which relates a galaxy's redshift to its distance. Yet, on top of this general expansion, galaxies also have peculiar velocities, local movements caused by gravitational interactions with nearby matter. These are typically small fluctuations around the smooth Hubble flow. In the late 2000s, a team led by Alexander Kashlinsky used data from the Wilkinson Microwave Anisotropy probe to look for patterns in the motion of galaxy clusters. They analyzed the kinematic Sunyaev-Zeldovich effect, a subtle distortion in the cosmic microwave background caused when CMB photons scatter off hot gas in moving galaxy clusters. This effect can reveal the peculiar motion of clusters relative to the background radiation. When the team examined the data from over 700 galaxy clusters, they found something strange, a bulk motion in a consistent direction, extending out to at least 1 billion light-years. This motion was not small. The galaxy clusters appeared to be moving at velocities of 600 to 1,000 kilometers per second, all toward a region near the constellations Centaurus and Hydra. What made this result startling was the scale. Motion on this magnitude and coherence over such a vast distance was not expected. According to the standard LCDM model, the cosmic microwave background should mark a kind of equilibrium. Large-scale motions should average out, especially over such distances. Yet this flow persisted, suggesting a gravitational pull from something beyond the observable horizon. The term dark flow was coined to describe this phenomenon, not because it is associated with dark matter or dark energy directly, but because it is invisible and unexplained. The implication is that something outside our cosmic light cone, beyond the limit of what we can see, might be exerting gravitational influence on the matter within our universe. This idea is difficult to test, but impossible to ignore. If true, it suggests that our observable universe is not isolated, but connected in some way to structures or forces beyond our reach. Several possible explanations have been proposed. One idea is that primordial density fluctuations left over from before inflation might have seeded this motion. Another possibility is that massive structures, perhaps enormous concentrations of matter or gravitational wells, exist beyond our observable universe and are pulling matter toward them. In either case, the implications are profound. It would mean that the universe's structure is more extensive, more complex, and more interconnected than previously imagined. Some theorists have even suggested that dark flow could be evidence for the multiverse, that our universe is just one bubble in a larger cosmic foam, and that gravitational effects from another bubble universe are bleeding into ours. In this scenario, the motion we observe is not caused by matter as we know it, but by a boundary between universes, a region of overlapping physics where gravitational influence leaks through. Though speculative, such models offer a framework in which otherwise unaccountable motions like dark flow might be understood. The idea of motion beyond the horizon is not new in physics, but dark flow gives it a concrete observational foothold. However, as with all bold claims, it must be weighed against alternative explanations. Some scientists argue that the original detection of dark flow may be flawed. Measuring the kinematic Sunyaev-Zeldovich effect is extraordinarily difficult, involving tiny temperature shifts in the CMB signal, often less than a millionth of a degree. Such measurements are sensitive to noise, foreground contamination, and instrumental limitations. Subsequent studies using different datasets have produced mixed results. Some found hints of similar motion, while others failed to replicate the signal with the same strength. In particular, results from the Planck satellite did not confirm the same bulk flow observed by Kashlinsky's team. However, Planck's approach used different cluster catalogs and statistical treatments, which led to ongoing debate rather than definitive closure. As of now, the existence of dark flow remains contested, not disproven, but unresolved. If dark flow is real, then it forces us to confront the limits of our cosmic models. The standard model assumes isotropy and homogeneity, that the universe, on large scales, is the same in all directions and places. If a directional flow persists beyond what gravitational perturbations from known matter can explain, then either those assumptions are incorrect or something is missing from our understanding. That something might involve extra dimensions, unseen mass distributions, or even modified gravity theories. Alternatively, dark flow may not be cosmological at all. It might reflect subtle errors in the way we interpret large-scale velocities, or flaws in our cluster catalogs, or even interactions between galaxies and intergalactic plasma that we do not yet understand. These mundane explanations are often more likely than exotic ones, but each possibility carries its own burden of proof. Regardless of the final verdict, dark flow has already had an important effect.
It has expanded the questions cosmologists are willing to ask. It has inspired new experiments, new simulations, and new thinking about what it means to say that something is beyond the observable universe. It reminds us that our cosmic map, no matter how detailed, is still incomplete, and that motion, not just structure, can reveal the hidden architecture of space. Perhaps the most unsettling aspect of dark flow is its directionality. Unlike most cosmic features, which are statistical and isotropic, dark flow suggests a preferred direction. This flies in the face of cosmic symmetry. It hints that the universe may have anisotropies, large-scale features that introduce direction or orientation on the grandest scales. If such features exist, they could reshape our models of inflation, structure formation, and cosmic fate. Yet, paradoxically, this direction also grounds us. It offers a vector in the void, a faint arrow pointing to something unknown. Even if the motion is not ultimately real, its study has opened a corridor in the conversation about the cosmos. It has raised new standards for precision in observation and theory. It has shown us that even at the edges of knowledge, motion continues, and in motion there is meaning. The effort to confirm or deny dark flow continues. Future missions with better angular resolution and deeper cluster catalogues may yet detect consistent signals or disprove them entirely. Projects like the CMBS-4 experiment, or gravitational wave detectors sensitive to large-scale dynamics, may help settle the question. Until then, the flow remains, at least in possibility, a whisper from beyond the cosmic curtain. And even if dark flow is ultimately disproven, it leaves behind a valuable legacy, a reminder that the universe may be more than we can see, more than we can currently measure, and more than we can comfortably predict. It invites us to imagine gravitational landscapes stretching beyond the reach of light, where cosmic rivers flow unseen, and where the rules we know may bend to possibilities we haven't yet written down. The story of dark flow is not a conclusion, but a current, a path into new questions. It does not offer closure, but momentum. It carries us, like the clusters it describes, in a direction we cannot fully chart. And in that motion, in that pull toward what lies beyond the known, science finds its truest direction, forward. As we draw this exploration to a close, we return to the vastness of what we have just journeyed through. Superclusters, spanning billions of light-years, voids so deep they mute starlight, waves frozen from the early universe, and the cold traces of questions still unanswered. The cosmos is not only large, but layered, built from ripples, flows, walls, filaments, and patterns too vast for any single perspective. And each of these structures, from the closest cluster to the faintest dark flow, challenges us to look deeper. Thank you for walking this path through the universe's greatest structures. Thank you for allowing the calm of science to settle into your night, and thank you for listening, because even in the silence of space, there is always something waiting to be understood.